Testing.
If it works.
Testing. Am I coming through all right?
I think you just have to turn on.
Awesome.
Oh, okay. Sorry, no, I was at the wrong.
Is it the
one.
best?
Yeah, that's good.
Okay. Okay, looks fine.
Audio's coming through okay for me?
Okay, so probably there's still somebody missing, but I mean, don't have much time. It's a busy afternoon. So Matt, the last lecture, sadly, I have to say, no, it was very nice. So please.
Okay, thank you very much. Yeah, it has been a hell of a week, and we're going to try and wrap things up as best we can in the hour that we have. I realized that there's no way that I can finish the storyline I wanted to share with you guys completely on the Blackboard. But at the same time, I'm really happy with the foundation we put together, because now I think you'll have some basis for when I start to tab through the slides and point things out sort of a more high level. The danger, of course, of the PowerPoint talk is that I get super excited and just keep going. Please continue to stop me, interrupt me with questions. That's still okay, just like before. Okay, so last time we did a couple of calculations. The second calculation that we did was the radiative process quark goes to quark plus a small x gluon. X here meaning the momentum fraction k plus over p plus, so that this gluon is radiated at mid-rapidity and not in the beam fragmentation regions of either the projectile or the target. Light front coordinates were a really helpful tool to do that. We found something really interesting, which was that in Kinematics, the high energy scattering, that there was a very delicate cancellation of initial state and final state radiation, that essentially kinematically the two processes were identical. At the amplitude level, they produce radiation that sits directly on top of each other, and they differ by a minus sign, that minus sign coming because the propagator in one case was space-like, in the other case it was time-like, and that was the difference between initial and final state radiation. That resulted in 0, so that QED at high energies is boring. You have no photon radiation if you don't shape the electron to accelerate it. But quarks, on the other hand, are free to radiate even if they don't accelerate kinematically because they're non-abelian particles. They interact by rotating in color space even if they don't reflect and scatter. And that's why the high energy kinematics is uniquely sensitive to the non-abelian nature of QCD. And sort of we ended on this teaser that we've set up now a competition between the smallness of the coupling constant in QCD and weak coupling and the largeness of a phase space logarithm. Here, this log of the center of mass energy is just the total rapidity interval. That if you have a soft gluon being radiated, you essentially radiate gluons uniformly across mid-rapidity. So now I want to walk through what are the implications of this and why do we talk about X? Because the entire discussion yesterday was about high energy QCD and had very little to do with X. So let me start off by taking a bit of a detour to give you an introduction to deep inelastic scattering. I'm sure many other people here already and later on in the week will, or next week will tell you more about this. But this is my high-level overview. Whenever I talk about deep inelastic scattering, I always like to make the analogy between what we understand about the structure of the proton and what we understand about the structure of the atom. The proton, like the atom, of course, is not a fundamental particle of nature. It's a bound state made up of quarks. And the structure of the proton comes from the nature of the QCD interactions. So in exactly the same way that QED generates all of atomic structure, all of chemistry, and we learn something about QED by studying in detail the fine structure, the hyperfine structure of the hydrogen atom. If we want to learn about QCD, one of the best ways we have to do it is by studying the structure of the proton. It's no accident that the proton and the hydrogen atom were both discovered simultaneously about a century ago. Once we finally had high enough energies to start peering inside materials, the Rutherford-Gold's foil experiment, of course, famously looked for high Q² scattering, high recoil particles. And just like in deep inelastic scattering, that high Q² backscattering is the signature that you interacted with something point-like at short distances. In the century since we have discovered the proton and the atom has grown up, right? So our understanding of QED, our ability to predict the structure of the atom, is at an astronomical level of precision. This is just a random paper that I pulled that I found at one point. Blows my mind. A calculation to 4 loop Feynman diagrams, 891 of them to 1100 digits of precision for the anomalous magnetic moment of the electron. Like, this is incredible. Like, one of the greatest triumphs of theoretical physics ever. Our understanding of QED is so precise, we literally use it as the definition of time itself. We understand the hyperfine slitting of cesium so well that that is now the most accurate definition of the second according to the National Institute of Standards and Technology. And in contrast, we understand QED so well that the theory has reached maturity, but the proton still is a moody teenager saying you will never understand it. And we do not even understand where basic properties of the proton emerge from its fundamental constituents. The proton spin puzzle, the proton radius puzzle, the proton mass puzzle. This is the one that I was referring to, where if you can suddenly solve from the QCD Lagrangian how protons and neutrons fall out, you instantly win $1 million because it's one of the millennium problems. I showed you these slides before. The fundamental difference between QED and QCD is one tiny change in the gauge structure of the theory. The fundamental ingredients look like Maxwell's equations, particles and fields, but in QED you have only one kind of charge. But in QCD, the non-abelian nature, the fact that you have multiple independent directions, directly leads to self-interactions of gluons. The self-interactions of gluons directly lead to confinement. I don't think this plot has been shown yet at the school. This is the heavy quark potential, very famously. This is the gluon-mediated interaction potential between two quarks that are so heavy that they're fixed in place. This is an early lattice calculation. You see very nicely the attractive 1 over r Coulomb potential at short distances where asymptotic freedom works. And you see it transitions to a linear potential instead of flattening out to 0 like the Coulomb potential does. The linear potential is of the form sigma times r. Sigma has units of force, and sigma is called the string tension. It has a numerical value of about 1 ton. So that's the statement. If you try to rip 2 quarks apart, you have 1 ton of force between them that never gets smaller. And of course, that means you can't just ionize a quark out of the proton if you want to measure proton structure. It's not that easy as we would use to measure atomic structure. So in exactly the same way, you cannot take a bar magnet and break it apart and find an isolated north and south pole. You cannot break apart a hadron into its constituents. You end up with smaller bar magnets that have the same properties as before. So we have to work a lot harder to study the structure of QCD compared to QED. And we see the differences between the theory of QED and QCD directly in our particle detectors. This is an event display from on the left. It's supposed to show electron-positron come in along the beam axis. Here they've collided and they make exactly one absolutely beautiful muon pair, mu plus, mu minus. So it's exactly 2 to 2, gorgeous. But then you do proton-proton scattering and there's a whole bunch of stuff that comes out. QCD is messy because of confinement. So where does a particle accelerator come in? You want to measure proton structure. You want to learn what's inside the proton. Normally, we talk about a microscope. A microscope, as we normally think of it, is an optical microscope, which is, of course, limited by the wavelengths of visible light. Visible light is a few hundred nanometers at most in the deep UV. And so that's a minimum energy of, say, 2 eV for your measurement. Something more powerful than the optical microscope is an electron scanning microscope, which is just a tiny particle accelerator. It's a thermally generated beam of electrons where you measure the scattering of the electrons and reconstruct images of things much smaller than that optical limit. So it's really not a big conceptual jump at all to go from scanning electron microscope to Electron-Ion Collider. It's exactly the same principle of using the scattering of the electrons to reconstruct images, but now there is no maximum energy in theory. It's whatever you can put together into your particle accelerator. The most root S you can get gives you the most resolution of proton structure. So deep inelastic scattering began with the SLAC MIT experiment in 1968. This is what helped us discover QCD in the first place. I'll walk through some of the logic that led us there. The current apex of deep inelastic scattering in terms of energy is Hera. Hera was the highest energy and the only proton-electron collider thus far. It ran until 2007 at a center of mass energy of 318 GeV. And of course, we're looking towards the future for the Electron-Ion Collider, which doesn't have quite as high of energy as Hera, but has a lot more flexibility in terms of polarization control, ion species, as well as much higher luminosity. Okay, theory of deep inelastic scattering. Now I finally will have the ingredients to tell you what X is. We've talked a lot about how gauge bosons interact with each other. They always interact by coupling to some kind of conserved current. And in the case of QED, that's the electromagnetic current that we studied before. So if I have inclusive electron-proton scattering, my observable is electron plus proton goes to scattered electron plus anything else. Could be a proton, could be a bazillion particles. They all get counted the same way in my observable. The basic process as a Feynman diagram looks like this. I've got electron and proton coming in. The electron interacts by QED. I know exactly how that behaves. The electron radiates a photon. The photon does something in the proton, and then the proton maybe comes out intact, maybe it blows up. Whatever it does, that's described by the interaction of the photon with the proton. And so here's an example of an event display from Hera. You see very cleanly the two sectors shown there. Electron comes in, proton comes in, you see the backscattered electron. That by itself is enough to allow you to totally reconstruct the kinematics of what did you throw at the proton from that photon and what came out. And you also see the spray of hadrons that comes out when you shatter the proton. The beauty of inclusive deep inelastic scattering is you don't have to touch that at all. If you do, you get more information, but the theory becomes much more complicated if you want to disentangle transverse momentum dependent parton distribution. But if all you need is a one-dimensional picture of proton structure, it's sufficient to just reconstruct the scattered electron, which is much cleaner. So we talked at a theory level before about the coupling of the photon to the conserved currents. I can say in general, even if I don't know anything about QCD, that the nature of that interaction comes in the form of photon that was delivered from the electron and some matrix element of the electromagnetic current. If I had no idea what QCD was, I could still write down a matrix element of this form. So that's my scattering amplitude. Now I know I have to square the scattering amplitude and integrate over some phase space to get the cross section. The amplitude squared now looks like this. Now I've just dropped the electron because the QED part of this process is really simple. That's so simple, I can write it down in one line, calculate it all out, and it's no. This is an uninteresting part of the process. Really, for me, the electrons are just a source of photons. And the details about energy that didn't come through the photon is just kind of an inefficiency for me. So I don't really care very much about inelasticity Y and things like that. Those are just losses that didn't actually contribute to scattering on the proton. The relevant part of the process is just the scattering of the virtual photon on the proton itself. Question? Yes, ma'am.
It looks like the vertexes are included in the Electron term. That's true, or am I mistaken?
Maybe you mean the factors of the electron charge. So those have been factored out, yes, and they've been pulled out up front by convention. The vertex is still there in the form of the gamma mu coupling. Is that what you're referring to? Yeah, so I mean, the vertex is still there, but you're right that in convention they factored out the coupling constants and they've just gone in front. So the relevant part for studying QCD is this piece, the Hedronic Tensor. We said at the amplitude level, I get a matrix element of, I started in the proton, I hit it with a current, and then I have X, anything in the final state. Well, if I sum over X, I have a complete set of states. So it makes perfect sense that the amplitude squared, after I remove that complete set of states, X in between, is a correlation function of two electromagnetic currents. You can think of it really as if this was a forward amplitude saying, this photon excites a quark inside the proton, and then it de-excites by radiating that photon. It's a little bit of a fictitious analogy as if this was a forward scattering process, but it's literally true in the sense of the optical theory. So I wanted to motivate, what are you learning? What is this matrix element? Without knowing anything about QCD, we know that deep inelastic scattering tells us about electromagnetic correlations inside the proton. As far as what kind of structures this can take, well, that's strongly constrained by Lorentz invariance. This process, after I've taken away the electron, only depends on two variables, P and Q. It's just the proton and the photon you're hitting with. So I have a tensor valued function, W mu. It's got two indices running around. It's a function of two momenta, P mu and Q mu. There's only a few ways that I can combine P and Q to get two indices upstairs. Everything else has to be an unknown function of invariance. And there's only a few invariants that I can construct. So the natural thing is, if I don't know anything about this function, at least let me decompose it in terms of unknown scalar functions called structure functions. Yes, ma'am.
So in the hadron tensor, the only place that we see the interaction with the virtual photon is in the e to the iq.x term, is that right?
The interaction with the virtual photon is the coupling to the electromagnetic current here. So the vertex was J mu A mu from minimal coupling. Here's the J mu. The A mu went into the propagator, and that now is the 1 over Q to the 4th of 5. So before we knew anything about QCD, we could have already said this much. So now I can finally define what X is. The relevant QCD part of the Hedronic Tensor depends on two invariants. It depends on P and Q, and I can make two scalar invariants from those momenta. I can take the photon momentum Q and square it. Q is a space-like momentum. So if I take the 4-vector Q and square it, I get a negative number. Conventionally, we just take the absolute value of it, and we call that capital Q squared. In terms of scattering kinematics, this is directly related to the energies and the scattering angle of the electron. So you see, the larger the scattering energy, the larger the Q squared, the larger the recoil angle, the larger the Q squared. Q squared, since it's a space-like variable, you can always go to a frame where Q squared is a transverse momentum scale. So that means Q squared is effectively a transverse resolution. If Q is a transverse momentum, then 1 over Q is the transverse position resolution information. So that's sort of the standard intuition we have for what DIS is telling us, that Q squared tells you whether you have deep inelastic scattering or like regular elastic scattering. If Q squared gets very large, then you're actually looking inside the proton. If Q squared is much larger than the mass scale of the proton, so much larger than 1 GeV, then the length scale that you're measuring the proton over is smaller than the proton itself. So if I do deep inelastic scattering, I see a hard scattering event just like Rutherford scattering, and I say, oh, my Q squared was 5 GeV squared. And then I know for sure that I hit something charged, some electromagnetic constituent inside the proton. So the story about Q squared is pretty well known. The story about X is much less so. X is another independent variable that you can make. If Q squared is a transverse variable, X is a longitudinal variable. X is something that involves a comparison of P with Q. So you can define various combinations. The scale nu is a similar scale, but X is the one that has sort of stuck around. You can again relate this to the transverse momentum divided by the energy transfer in the rest frame. That's all well and good, but what does it mean? The simplest interpretation that I know of for Bjorken X is in terms of a time scale known as the Yoffie time. If I go to the rest frame of the proton, then this time scale, 1 over m times x, is the time scale of the interaction of the virtual photon. You can already see that here at the level of the definition of the Hedronic Tensor. So Bjorken X enters one of the components of Q. And that component of Q tells you about how separated these two currents are. It's related to the Fourier transfer. So it's literally a case of this point and this point are separated along a light-like direction by the Yoffie time. And as X gets smaller, those two vertices start moving further and further apart. If X is a number of order 1, then these two things are sort of inside the proton. And you have a simple picture that looks like my photon hit a quark that was already inside the proton, puts it back in, and that's how I get a number operator measurement inside the proton. But things start to get weird when X gets small. When X gets small, that resolution time gets longer and longer. And that means that you're able to resolve shorter and shorter lifetime quantum fluctuations. So one way of thinking about it is it's a boost factor. As you go to higher and higher energies, lower and lower X, you increase the time dilation effect on quantum fluctuations. So you're able to resolve things that used to look like just 3 valence quarks in the proton. Now at smaller X, you can see, oh, it was valence quarks and soft gluons. And if you keep dialing down X, now you see more and more of those quantum fluctuations. So in this analogy, the deep inelastic scattering is a camera or a microscope. I would say Q squared is your resolution. That's the number of pixels you have. X is related to your exposure time or your shutter speed. That's how fast you're able to take the picture and what particles you're able to see based on how long they live. Question?
Yeah, could. That's not my question. Yeah, can you go back to the last slide?
Sure.
Okay, so you've kind of like taken the two diagrams.
Yep.
But that's not like really what's happening, really, like some other final state is coming out, like either proton or some.
Right, so this is at the level of the amplitude squared. So this is a Feynman diagram, if you like, for the cross section, coming from squaring the particular diagram. Yes.
So could you look at the Yoffie time as like the time that it takes the, internal quarks to rehydronize?
I'm not sure about that. The thing that I know for sure is coming from this Fourier transform. So I know the Yoffie time having a simple interpretation at the level of the amplitude squared. I don't know if I could get a simple interpretation at the level of a single amplitude. Sorry. Okay, so that is what X and Q squared are. This is what we saw when we got our first peek inside the proton. So these are actual plots from the Nobel lectures from Friedman, Kendall, and Taylor, who were on the SLAC MIT experiment. Without knowing anything about QCD, if I just take that Hedronic tensor and I decompose it into all allowed structure functions, there could be two called F1 and F2. And a priori, both F1 and F2 could depend on both of the kinematic invariants, X and Q squared. So when they actually did the SLAC MIT experiment, they found two critical pieces of information that in fact you don't have as many independent variables as it looks like. For one thing, F1 and F2 are not independent, they're related to each other. The ratio of F1 to F2 is this fixed proportionality as soon as Q squared starts to get bigger than about 1 GeV squared. The particular value that they converge to here is exactly the value that you expect if whatever the electromagnetic constituents of the proton are spin 1/2 fermions. This is referred to as the Callan-Gross relation. And that's part of how we know that quarks are real. We see that inside the proton, you are hitting something which is a spin 1/2 point-like charged particle. which just so happens to be what we expected in the form of quarks. If there were different spins, like if they were scalar constituents inside the proton instead of fermions, then you would still have a relation between F1 and F2, but it wouldn't be this relation, it would be a different relation. So this particular form of the Callan-Gross relation gives us evidence that quarks exist as spin 1/2 fermions. The other thing is that not only are F1 and F2 not independent, they don't depend on both kinematic variables. They could depend on both x and q squared, but at least at the kinematic reach that they had at SLAC MIT, they only depend on x. They are independent of q squared. And this is the phenomenon of Yorkin scaling. If I take this literally, if q squared is my resolution scale, and it doesn't depend on the resolution scale, that's weird. It looks like the quarks are point-like at every resolution. As soon as I see inside the proton, I see point-like particles, and I can zoom in as much as I want, and they're still point-like. That's okay unless you know something about quantum field theory. And quantum field theory says that should not happen. That's exactly the opposite of what happens in QED, as we've discussed. Fluctuations are allowed to blow up to infinity at short distances. So why is it that it is point-like at all scales? If I zoom in, I should see more and more quantum fluctuations going crazy, but we don't. And if quantum fluctuations are allowed to blow up, but they don't, the only explanation is the probability of those quantum fluctuations is going to 0 at short distances. And that means asymptotic freedom. So the observation of Yorkin scaling demands a theory which has asymptotic freedom to explain why it is point-like at all scales. And this is what led us directly to QCD. Once you know I need something with 3 different color states to describe the omega minus baryon. Oh yeah, free quarks don't happen to show up in my detector. Things are point-like at all scales. The one piece that brings it all together is an asymptotically free theory. And as soon as you know number of colors is 3, that pretty much uniquely gives you QCD. So that was our first picture of what's inside the proton. This is a modern picture of what's inside the proton. This is an extraction of the parton distribution functions, number densities of quarks and gluons inside the proton as extracted from HERA, here shown as a function of x. This is probably familiar to everyone, but let me point out a couple of important features here. There are 2 very different regimes of proton structure. The one that lives at large x is the one that we normally think about when we think of the proton. Our naive picture of the proton is it's made of 3 quarks, 2 up quarks and a down quark. And you know, that's literally true to a certain extent. In the region where x is large, there are predominantly up quarks and down quarks. There are about twice as many up quarks as down quarks. And if x is a momentum fraction, then if all 3 quarks were just sitting statically at rest inside the proton, then they should all share an equal fraction 1/3 of the proton momentum. And yeah, you know, the peak of these guys is pretty close to 1/3. So this picture of the valence proton is true in a certain region, but it is not the whole story. That valence picture of the proton, if you look at the position of the peaks, it's actually downshifted slightly from 1/3. That's because QCD is a dynamical theory. And even if you start off with 3 quarks happily sitting at rest, they're going to start interacting and radiating gluons. And all of the radiation that comes off of that is going to bleed energy down and take energy away from those valence quarks. So what you see is 2 different distributions, the valence structure of the proton and the radiative structure of the proton. As we've seen, QCD loves to radiate gluons, even quarks that have low momentum fractions. So this radiation distribution has a high density of gluons, also C quarks, each of which has a very tiny percentage of the proton momentum. So you have 2 up quarks and a down quark that carry, I don't know, 20% of the proton's momentum each, and the rest is in a cloud of radiation. This tells me that depending on where I look at the proton, I could see 2 very qualitatively different pictures. The proton at large x is a dilute system, where I can have this picture of 1 quark gets knocked down, I have coherent color lensing that pulls me back towards the other quarks, and maybe that's my explanation for the Sievert's function. But that explanation doesn't make any sense in the dense proton, where I've got billions and billions of gluons, and the color interactions are much more complicated. So I wanted to emphasize here that already at the level of deep inelastic scattering with a focus on q squared, we see that something weird is happening at small x. If I take the agnostic approach that says, I don't care about small x, everything is d-lab, everything is q squared. You can get a lot of mileage out of that. You can extract the PDFs. You see the structure functions are starting to blow up, but you can still fit them with dglab. But if you really dive into the fits, you see that something systematic is happening at small x. This is an NNLO fit based on dglab only. And you see that the chi-squared of the fit, the quality of the description, systematically degrades as you include more and more small x data. This is telling you that just the dglab fit, something that ignores small x physics by itself, starts to have problems describing the data. The data requires something new coming from the small x region. And the thing that it requires is leading log x resummation. This is exactly BFKL, which we talked about last time. So if you start to include these large logarithmic effects, you stabilize the chi-squared. Now, this is far from a smoking gun, I would say, but I'm happy that there's clear evidence I can point to from DIS itself that says you cannot describe everything with dglab even if you try. You have to have something else from small x. So what is the something new in small x? The picture of DIS at large x is usually drawn as a handbag diagram. I would call this a knockout process, where your idea is, I have some quarks inside the proton, and I hit one of them really, really hard with a photon, and that quark goes flying out. That's fine. That's perfectly good for kinematics where x is largish. Let me go back to that picture here. And I'm interacting over a distance that's inside the proton, right? Like I have to hit it where there are quarks to kick out. Now, when you go to small x, however, something gets weird about those kinematics, right? The distance between electromagnetic current number 1 and current number 2 starts to get much larger than a Fermi. And then that interpretation of, oh, I just knocked a quark out of the proton doesn't make a lot of sense anymore. You're interacting over much longer time scales than the size of the proton itself. The solution to this conundrum is that the electromagnetic current can do more than just knock out a quark. It can also cause pair production. So I can have photons that are very, very far away from the proton itself that interact electromagnetically far in the past or far in the future. That electromagnetic interaction of the photon can create a quark-anti-quark dipole. And then the thing that hits the proton is not a photon at all. It's a baby proton-proton collider. It's a tiny hadronic system made up of quarks, which is overall color neutral, that is then scattering on the proton. So DIS at small x changes radically. It no longer looks like a handbag diagram, a knockout process. This one is technically an NLO process, right? It's got an extra vertex in it to let you fluctuate and then scatter. But paying an extra price of alpha s is no big deal compared to running out of quarks. This expression is power suppressed at small x. This expression is only suppressed by 1 factor of alpha s. So at small x, you change the leading behavior of DIX. You change it from being handbag knockout kinematics to small x coherent dipole scattering kinematics. So when you do that, you turn DIS, you turn photon-proton scattering into something that looks like a hadronic collision. It looks like quark-quark scattering, which we just calculated. The relevant degrees of freedom are now highly boosted, highly Lorentz contracted. Right, so these guys have long lifetimes. The phase of the dipole that's propagating through the quark, propagating through the proton field, isn't really changing very much during this very small interaction time. So what you have is essentially a coherent phase, a coherent line integral. This could include one gluon exchange. This exponential, if you expand it back out, is just one vertex IgA+, exactly the Eichenal vertex that we used when we calculated quark-quark scattering. But the exponential allows you to have many of them, not just one gluon, but 2 gluons, n number of Eichenal gluon exchanges. Yes, sir?
So the photon forms a Q-bar pair.
Yes.
But then you're calling that a proton?
I'm making the analogy that this now is a hadronic collision mediated by gluon scattering, exactly as when we did quark-quark scattering yesterday. That's very different from something like this, where you have T-channel quark exchange. Here you have the quarks are coming in the S channel from minus to plus infinity, and the dominant dynamics is gluon exchange, exactly as before.
It's an asymmetric collision, right? Why are you calling the Q-bar to be proton? Shouldn't it be some other like mesonic pattern?
Yeah, it's not literally a proton. I'm making a metaphor to say that this is something smaller than the proton. Maybe this would get some traction then. There's a big story of small systems in heavy ion collisions. We say, oh my God, I'm making the quark gluon plasma not only in gold-gold collisions, but also in deuteron-gold collisions, maybe even proton-proton collisions. When does it turn off if I go to small systems? Well, you don't have a smaller system than the proton, maybe the pion if you work really hard. This is a system which is a smaller system than the proton. So the Electron-Ion Collider is the vehicle for doing small system scans that allow us to continue the question of when the QGP turns off. This is a small hadronic system of arbitrary size. And in fact, I can select on whatever size I want because the size of the dipole is controlled by Q. So I can go to the EIC and say, I want a system smaller than a proton. Do I still have collective flow or not? And just by bidding in Q squared, I can dial on these quantum fluctuations. So the point is that the modality changes. It goes from being quark knockout to gluon scattering, exactly as dominates proton-proton collisions, exactly as dominates heavy ion collisions. Yes, ma'am? Sure.
When you say large X, do you still mean less than 1?
Yes. So the things that I call large X are probably quite different from what most people at JLab call large X. When I say large X, I mean X of order 1. Large X to me is something of order 1. So I'm thinking things like X is a half or X is a third, things that live in the valence region. I do not necessarily mean that X is asymptotically close to 1. That's the more stringent condition that 1 minus X is a small number. This I'm not talking about, this I am. And second?
So the small X with the quark antiquark, can you look at that as pionic? Or is that a
Pion has a certain set of quantum numbers. This is a vector particle, so to speak, because it comes from a fluctuation of the virtual photon. Maybe a good example is if I make an exclusive process instead of an inclusive one, I can say, what's the probability for that photon to come in and maybe a J psi to come out? Then you really are selecting on photon creates a charm-anti-charm pair, and then the charm-anti-charm pair coalesces into a J psi device. So it's some kind of vector meson. It doesn't necessarily interact with itself long enough to actually form a meson, but it has some probability of doing so. Okay, other questions? Yes, sir.
Yeah. So you said at the beginning that the advantage of having EIC is that it's a clean environment.
Yep.
But now you're telling me that with a photon, you're creating actually hadron, virtual hadron.
Yep.
So it's not so clean anymore.
But still a lot cleaner than if you had proton-proton collisions or ions, all that stuff. Yeah.
Okay.
And I'd say most importantly, the QED type interactions are factorizable and controllable here. There are actual factorization theorems that continue to hold even at small x, which we just don't have the advantage of for PP and heavy ions. Okay. There's a lot of hand waving that gets passed off as science in hadronic scattering, and you can't cheat like that when it's EA collisions or ET collisions. So the main point here is that there is something fundamentally different about DIS at large X and at small x. It literally changes the scattering modality, and the relevant degrees of freedom change. The relevant degrees of freedom for this kind of scattering are Wilson lines. Ipinal high energy quarks, antiquarks, gluons, but something whose root S is going to infinity, and that who rams through a background field of gluons. Depending on how many gluons you have there, maybe you can just truncate the expansion and maybe only single scattering matters. Or maybe you have to include double scattering. Or maybe these are non-perturbative gluons, and you have no ability to truncate the series at all. Then you just have to stick with the line integral, whatever it may be, and you have no ability to do the expansion. So this is the natural language, the natural variables that one uses to describe DIS at small x, or any process at small x for that matter, since DIS at small x is exactly the same as proton-proton at small x. So the relevant variables are everything that you can build out of Wilson lines. The simplest object that I can make out of Wilson lines is a single dipole trace. So if I look at this amplitude squared, I have the photon, it creates a quark that has some color flow, goes through into the complex conjugate amplitude where it's removed. The anti-quark flows back the other way. This is a closed loop of color flow. That closed loop of color flow is nicely gauge invariant, so you can calculate it in whatever setup you want. And the relevant degree of freedom is this dipole scattering amplitude. So this is literally the S matrix for the interaction of a quark-anti-quark dipole in a background of the gluon potential of whatever your target is. So when we start talking about DIS at small x, or any process at small x, it's dipoles, dipoles, dipoles all day long. So I hope this is starting to look familiar. We worked very hard to construct the elastic scattering baseline of quark-quark scattering. This is just the leading part of the Wilson line. This is the single gluon exchange, which is the first non-trivial part. If you now staple on two gluon exchange, which is eigenval, it's not really much more complicated than one. And if you resum all n of them, you get exactly the Wilson line of the previous slide. And we saw that once you have Wilson lines, eigenval scattering, this is not the whole story. Radiative corrections can change the energy dependence because they start to introduce large logarithms coming from the huge rapidity available to radiate soft gluons. So the next natural step is, if I know I need to build DIS out of Wilson lines, then I need to start calculating small x radiative corrections to the Wilson lines that are going to generate more and more complicated operators. Yes, ma'am?
What's the Wilson line?
The Wilson line is this. This is the path-ordered exponential. So think of it like a WKB approximation. So it's a semi-classical description. You say, I've got a particle at point X, it goes to point Y, and it goes through some background field. So the Wilson line, another way to say it is, this is literally the propagator of a quark moving through a background field. So a Wilson line is V of X perp equals, I have a quark which is going through, it's at transverse position X perp, and it undergoes one gluon exchange with an external potential A plus, another gluon exchange with an external potential A plus, any number of those. So the Wilson line doesn't, I don't have to say what A is. Whatever A is depends on what the target is. But I know that a high energy quark interacts with that background field in a very simple way because eigenval kinematics are really simple. Wilson lines, by the way, are also the correct description for high energy particles like jets. If you want to describe a jet going through the quark gluon plasma, you do it exactly this way. It's a high energy jet which interacts potentially many times with the background field, whatever that background field might be. Other questions so far? Okay. So if the DIS cross section changes qualitatively when you go to small x, so do the PDFs. The PDFs and the cross section are related one-to-one by collinear factorization. So if I know this cross-section changes from knockout DIS to dipole DIS, well, I guess my description of the PDF itself is also changing from being something that looks like psi bar gamma psi knockout process that looks like this to sort of an operator that looks like this. All right, a little bit of notation here. The thick blue bar represents the gluon field of the target. Essentially, in the high energy kinematics, all of these gluons are Lorentz contracted down so that they're a delta function in position space. They have zero width because everything's infinitely Lorentz contracted. So, that's what the blue shockwave is supposed to represent. That's where it hits the proton, that's where you go through the background fields. And if I now calculate all possible time orderings, I could have had, right, so the cross here is where the quark operator is. This is where the electromagnetic current is. So this is literally photon comes in, maybe the photon goes past and interacts over here and it pair produces there. Maybe it pair produces before and then I have actual quark-anti-quark scattering of the proton. And in general, I have all four combinations. It's a little bit weird, right? This is a non-interacting term. This is not a contribution to the T matrix, it's a contribution to the S matrix. But when I add up all of the contributions, that exactly cancels the non-interacting part of the Wilson lines. If I replace these guys by 1, I get 0 as I should. So summing over all of the time orderings gives me an expression for the PDFs in terms of dipole amplitudes. And the other piece that connects them is the photon wave function, the actual probability which one calculates in QED. The actual probability of the photon to fluctuate into a quark-anti-quark pair. That's textbook material that you can calculate directly from the QED vertex. So then I can construct an expression for the PDFs in terms of an integral over the phase space of the quark-anti-quark dipole coming in. This is sort of an extra loop that I have to suffer through. It's a little bit annoying that there's an extra loop already at tree level before I get to the interesting dipole scattering physics, but so be it. The operator now that controls the energy dependence or the X dependence of the PDF are completely encoded in these dipole traces. So the problem has now been reduced down to calculate the scattering, the energy dependence of a quark-antiquark dipole interacting with the target, whether that target is a proton, a nucleus, something else. Any questions so far? All right, so let's set up the calculation to get those radiative corrections. We need something which is our initial condition before I start calculating radiation. The initial condition doesn't really matter that much. We can take it to be something simple. I could take it to be, for example, quark-quark scattering. I still have to have a dipole. I have my photon coming in, so I have a quark and an antiquark, but I can pretend my target is as simple as I want, just to have an initial condition for the evolution. So I can literally take the answer that we had on the board yesterday for quark-quark scattering, add in antiquark-quark scattering, and the sum of those two things has this form. Notice that it is energy independent, exactly as we calculated yesterday. It has some transverse dependence. Here it's all very natural to write it in transverse position space, not transverse momentum space, but they're just a Fourier transform away from each other. So you have some transverse momentum dependence, energy independent in the initial condition, just like we had before. Now the exercise is to calculate radiative corrections. So in this picture, I have Wilson lines. I've got a quark Wilson line, an anti-quark Wilson line, and what I can have is soft gluon radiation at a new transverse position x2. And that extra gluon that's getting radiated could pass through the shock wave and contribute to the scattering, or it could be a virtual correction, which it gets emitted and absorbed before or after. So my radiative corrections come in two types, real and virtual. The real correction, since the gluon passes through the shock wave, that means it was emitted before you hit the proton and it was absorbed after you hit the proton. Those change the operator. Before I had a Wilson line at position 0 for the quark, a Wilson line at position 1 for the anti-quark. Now I have QED vertex with color A, QED vertex or QCD vertex with color B, and now a Wilson line for the gluon. The gluon now also passes through the background field. You have a similar expression for the Wilson line of the gluon, but in the adjoint representation instead of the fundamental. So the main point here is when you have radiative corrections, if that extra radiated proton also scatters, well, I guess you got a more complicated operator out of it. If it doesn't scatter, you're lucky, and then instead you just get the same operator back. I started off with an equation for a dipole. The virtual correction is still a dipole. The real correction is something worse. So these are radiative corrections specifically where I've radiated and absorbed the gluon from this line number 1, particle number 1. Yes, ma'am.
Is it accurate to say that radiative corrections are photons for your electron, but gluons for your quark?
Yes, I think the big thing one worries about on the electron side are 2 photon exchange contributions. So in general, you could have radiation either off of the anti-quark line or radiation off the quark line, or you could have a mixture where the gluon is radiated off of one of them and absorbed by the other one. It's fairly simple when the radiation is coming from one particle and absorbed by the same particle. You might call these ladder emissions, because if I start chaining those things together, it looks like I had a quark and then I had a soft gluon, and then I had a soft gluon, and then I had a soft gluon. And you build a ladder out of these structures. The ones that are emitted by one particle and absorbed by another particle don't have that simple ladder type topology to them, but they're still trying. So the ingredients for this just come from the wave function, literally the light front wave function, just like we talked about before, for the quark to split into a quark-gluon system. In momentum space, that dependence is 1 over k perp squared. And if you Fourier transform it, it's just 1 over x perp squared. So this factor in red here is just the spatial part of the wave function. This first term, 1 over x21 is the distance between position x2 and position x1. So that x21 is that distance, and that distance is exactly the wave function of this splitting. So this term is exactly the term where the gluon is radiated off of particle 1, and it has the new position number 2. Likewise, if I radiate it off particle 0, then I get something sensitive to the distance x20, but it's the same distance in both cases. For the more complicated non-ladder type emissions, I could emit it off of particle 1, so I have 1 factor of x21, and I could absorb it on particle 0, so I've got 1 factor of x20. So these are all of my building blocks. When you stare at those ladder emissions, one thing starts to pop up that looks a little bit concerning. We said that these things have a transverse momentum or a transverse position dependence of the form 1 over x squared. Well, if I'm integrating d2x over x squared, that's logarithmic. Does that generate yet another logarithm that I've got to worry about? The logarithm that we talked before was a longitudinal logarithm, a rapidity logarithm, which came from that longitudinal momentum dependence. So if there is an extra transverse logarithm here, that's weird and that changes the power counting. But a miracle happens. That miracle is color transparency. The region where this thing starts to become logarithmic is when that distance x21 goes to 0. But if x21 goes to 0, then this is a teeny tiny fluctuation. And that gluon is sitting practically right on top of the quark that birthed it. And because of color transparency, for this case, when that gluon passes the shock wave, that tiny extra fluctuation that you added doesn't really interact at all. Because of that, there's no difference between the virtual correction and the real correction. And these guys cancel each other on the basis of color transparency. So even though it looks like, hey, that transverse integral is trying to become logarithmic, actually it doesn't, because the rest of the integrand goes to 0. You can see that clearly from the expression here. If I take the position number 2 and I put it equal to the position number 1, then I would have V1 dagger, that cancels, and then I just get 1. And then I would have trace V0, V1 dagger minus trace V0, 1 dagger, which is 0. This is the physics of color transparency, that if you have a tiny fluctuation, it hardly interacts at all, and therefore it cancels against the real and the virtual corrections cancel each other. I'm belaboring this point now because this transverse logarithm is exactly the one that comes back for the case of polarized evolution equations. And there it is not benign. There color transparency does not save you. And you do in fact get doubly logarithmic evolution equations, which are significantly more interesting than what I'm sharing with you now. Okay, so what does the final beast look like? Yes, sir.
Why do we call that color transparency? This is only a question about the terminology.
Sure. It's transparency in the sense that that the medium is optically transparent to the system. That you have whatever the shock wave is going through, and that this tiny probe has S matrix going to 1, I guess. So I think it's transparent in the sense of like optical thickness. I don't know if that helps or it's just a nomenclature thing. Thank you. Sure. Okay, so this is the whole result. There's this very nice relation that if I take both of these pieces, the ladder and the non-ladders, when I add them all up, they form a beautiful perfect square. I've got 1 over x21 squared, 1 over x20 squared, and a cross term with a factor of 2. So when I add them all up together, they beautifully combine into what you will always be able to recognize as the BFKO curve. This is the combination of wave functions that describe all possible emissions and absorptions of those gluons from a dipole. So this structure has the momentum dependence. It's nicely universal. The transverse integral is finite. So I don't have to worry about regulating this super carefully in the infrared or in the UV. It goes to 0 at short distances because of color transparency. It goes to 0 at long distances because the dipole is color neutral. The relevant logarithm, the one that we saw last time, is the one that comes out of this longitudinal integral. This z is the fraction of light front momentum components. So it's exactly like Feynman X. If I integrate this up to the maximum value down to my lower cutoff, I get a logarithm of the energy. And that's exactly what I would have if I had energy independent scattering magnitude. So if I take my initial condition, the calculation we did yesterday, these guys are energy independent. That integral gives me alpha s times a log. So this is the integral form of my evolution equation. This is referred to as the Validity hierarchy. This is the full form. And the challenge of this is I started off with one operator, which was the matrix element of a dipole. To solve that evolution equation, I need to know the matrix evolution of a double dipole. Well, I don't know the evolution of a double dipole. I got to go back and recalculate. So I start over. The evolution of a double dipole depends on the evolution of an even more complicated object. So this is not one differential equation. This is infinity differential equations. in which 2 parton scattering depends on 3 parton scattering, depends on 4 parton scattering. And if you want to solve this thing, you have to solve everything at the same time. That's really hard. I don't know how to do it. You can write it as a recursion relation in terms of operators. This is Validity hierarchy of increasingly complicated operators. You can also write it in terms of this arcane functional differential representation. This is what's known as the Jim-Walk evolution equation. These two things are formally equivalent to each other. They contain the exact leading logarithmic behavior at small x. But this is not terribly useful for my purposes because I can't solve it and I can't show you where the physics comes from. So let's look at 2 simplifying limits of this general equation. The first limit is the dilute limit. Right, so I have a dipole amplitude, and now I've got something which depends on 2 dipole amplitudes. If I've got lots and lots of gluons in my target, then both dipoles have a chance to scatter. But if my target is dilute, and each of these dipole scattering amplitudes is pretty close to unity, then I could expand, assuming low probability of interaction. So formally what I'm doing is I'm saying, this is my S matrix, 1 minus the S matrix is the T matrix. So I'm saying the scattering probability is small, T matrix is much less than 1. If I make that assumption in the general formula from before and I expand it all out, now I get something much simpler. This is built out of only dipoles. Basically, in this term, I can set this guy to 1 and keep this one, or I can set this guy to 1 and keep that one. This one already has a single dipole limit. That's how I get 3 terms, and thankfully, everybody is made out of dipoles. This is one closed differential equation which you actually have a hope of solving. I won't try to do it here, but you can solve it by Laplace-Mellin transform. Laplace transform was something that I learned in undergrad differential equations, never used again all throughout grad school, and then I had to rapidly relearn how to do it when I started working in this field. When you solve this, you get something quite remarkable. This is giving you the exponential growth as a function of rapidity of gluon density. So if you calculate this, so you solve this evolution equation and you ask, what is the leading behavior at high energy, or the leading behavior as x goes to 0? The solution is your PDF, actually all of your PDFs, doesn't matter if it's the quarks or the gluons, everything is growing at the same rate. They grow as a power law behavior of 1 over x as x goes to 0. When you solve this equation, you do the Laplace transform, you do saddle point expansion. Long story short, you can pull out a particular number in some leading approximation. That particular number is known as the Pomeranian intercept in the literature. That goes way back to the days before QCD with Reggie trajectories, where people said, whatever power is up here tells me about the effective angular momentum of the particle that we're exchanging. So that's what a Pomeran is, that's where it comes from. We built this out of gluons. This is the perturbative version of the Pomeran, where you can actually calculate it in terms of elementary QCD. So that is BFKL. What does BFKL do for us? Yes, ma'am, question?
Sorry, I think 2 slides back.
Sure.
Which term was the rapidity?
The longitudinal integral here, the dz over z. The z here is the fraction of plus momentum. So it's exactly like Feynman x. Right, so this integral dz over z, z is the fraction. If I had p plus was the original momentum coming in through one of the particles, zp plus is the k plus of the gluon that's coming out. So this dz over z is integral dk plus over k plus, which is integral over the rapidity, where rapidity is 1/2 log k plus over k plus. Sure. Okay.
Sorry, Matt.
So this is not the rapidity.
There are many possible versions of the rapidity. This is the momentum space rapidity. It's not the space-time rapidity, it's not the pseudo-rapidity, but it is the true rapidity of momentum.
Sorry, Matt. We
Yes.
have still 5 minutes for the lecture. That is
Okay.
probably very short. We can expand for 10.
Okay, but there are other lectures after this, and I shouldn't shortchange on this. Okay, so this was the main point that I wanted to show you about how the logarithms generate this increasing energy dependence, generate increasing gluon densities. We're essentially in this situation where if you solve the evolution equations in the dilute limit, starting at large x, the prediction is something which is growing exponentially as a function of rapidity y, or equivalently power law as a function of x. That growth cannot continue forever. Eventually, you fill up the proton with so many gluons, so much color charge that you can't just bram off another gluon and put it wherever you want. Eventually, nonlinear recombination effects become equally important to extra bremsstrahlung effects. And in that limit, you will turn over this exponential growth and cause a saturation of the density. That's what we're looking for here. This is actually already present in those nonlinear evolution equations. The full terrible version of the Validity hierarchy here is basically unsolvable as written. The other limit that one can take is a mean field approximation. If I could somehow take those angle brackets and split it up to get this matrix element times that matrix element, then I'm happy. It's a nonlinear equation, but it only depends on dipoles and I can still solve it. That's what the large NC limit does for us. I said before that the large NC limit simplifies the color structure. Indeed, it does. It makes the diagrams plainer. It suppresses gluon-mediated correlations between one dipole and another dipole. So you end up with an independent product of two dipole amplitudes. This is now a more complicated equation, but it can actually be solved. This is one differential equation, not infinity differential equations. When you solve this, you find that there is a characteristic momentum scale called the saturation momentum QS. It's essentially a new physical scale coming from the high density. The saturation momentum is proportional to the density of gluons. And that saturation momentum tells you physically the size of the color domains that remain. Basically, you say, I started off with some initial condition down here. Now I added in 1 billion gluons. And that random walk, it's literally a random walk in color space, in that 8-dimensional color space. That random walk process leads to random color screening. And so at a given value of X, your coherent color domains keep shrinking. And they have a particular size at whatever X you're at. The size of a color domain defines a length scale. 1 over that size is a momentum scale. This is the saturation momentum QS. If you plot the gluon distribution in momentum space, you find that it has a characteristic peak. This is the phase space distribution. There's a characteristic peak around QS, not exactly at QS. It agrees with that same power law tail at high transverse momentum, but saturation regulates the infrared. This is the miracle of it, right? Non-perturbative physics lives down here. Non-perturbative physics happens at lambda QCD. If lambda QCD is here, then I can do perturbation theory, and then when I hit lambda QCD, I give up. But if lambda QCD is here, I can do perturbation theory out there, and the perturbative saturation scale kills the infrared behavior before you hit lambda QCD. So it's a bit of a theoretical idealization, but if I can make the density high enough, then I can make QS a hard momentum scale, greater than 1 GeV. And if that's a perturbative momentum scale, then perturbation theory can tell me everything I need to know about the system. Because I can calculate at high momentum, and perturbation theory itself controls the infrared before you get contaminated by non-perturbative physics. Okay, so a couple of words in closing about why this is so important. This high density of gluons is extremely dangerous for the self-consistency of QCD, because in the linear evolution regime, that dipole amplitude is growing exponentially. That dipole amplitude is an S matrix. It's literally related to a probability. And so what you see is, as I add in more gluons, more gluons, more gluons, my scattering probability goes up. The S matrix of my dipole gets, I guess the T matrix gets closer to 1, the S matrix gets closer to 0. But that linear regime, the exponential regime of BFKL, that blows right past 100% probability and doesn't care. So the linear evolution equations are not tenable. The current experimental situation is not tenable. We have evidence that there is linear leading log evolution. We see the exponential growth. That cannot be the whole story, because if it was, you would shoot right past 100% probability and your quantum field theory is broken. So something that controls that growth and forces you down to 100% probability is mandatory for a well-defined theory like QCD. If you solve the BK evolution equation, you see exactly how that works. It slows down that growth. The growth is exponential in the beginning, and then it slows down. You see that it asymptotically approaches 100%, but it never gets there. This is what I would refer to as the little unitarity problem, right? BFKL evolution drives you right past 100% probability at a point. Nonlinear evolution, BK, solves the problem of 100% probability at a point, but it doesn't solve the problem of total unitarization of the theory, because even though I might correctly saturate to the black disk at a point, the whole region inside the proton is slowly getting there. So the radius of the black disk is growing as a function of energy too. Even though I guarantee that each point doesn't shoot past 100% probability, the integrated probability might still be growing too fast. That is sensitive to non-perturbative physics. That's something that perturbative QCD can't solve for. But the little unitarity problem is something local in position space. This is something that perturbative QCD can answer. And you must solve this problem. You must solve the small unitarity problem, or else you have no hope of solving the big unitarity problem. So saturation is mandatory. Gluon saturation in some form must exist. Otherwise, QCD is not a unitary theory. It does not satisfy the little unitarity constraint. So the reasons that are usually given for why should I care about small x is, oh, look, I can create an exotic state of nuclear matter. It's like a gluon laser where all the gluons are coherent with each other and they have the maximum intensity allowed by nature. That's all true and that's all really cool. They're also important for initial conditions of heavy ion collisions. If you want to discover the quark gluon plasma, you've got to disentangle or discover the properties of the quark gluon plasma. You have to disentangle the final state interactions from the initial state interactions. And two colliding nuclei, which are themselves already at high density, could well be in this saturated regime. So you might need a saturated gluon phase, sometimes called plasma, in your early stages of a heavy ion collision. Yes, all of that's true, but for me, that's not the most important reason. For me, the most important reason is the one that I shared with you yesterday, that this explosion of gluon density is an inevitable consequence of a non-abelian gauge theory. If you have a non-abelian gauge theory, anything which is beautifully asymptotically free, just like QCD, as soon as you have this, you have a non-abelian gauge theory with commutators. As soon as you have commutators, you have a rapidity-independent distribution of soft bosons. As soon as you have soft gluon radiation, which is constant in rapidity, you have large logarithms. So exactly the same feature that makes QCD awesome, UV complete, our best candidate for a grand unified theory of nature, also threatens to blow it up. The same feature that gives you UV completeness here could destroy UV completeness there if saturation doesn't exist. So in my opinion, we need to know whether saturation is there or not. We believe it should be there. We haven't seen it yet. But if it's not there, then QCD is broken irredeemably, right? If we're just wrong and saturation is not there, then QCD does not satisfy a unitarity condition and QCD is not self-consistent. And not just QCD, every non-abelian gauge theory will have this problem. I don't know anything about Technicolor, but I guarantee you Technicolor has a saturation problem. And whatever UV complete theory of nature you're dreaming up, you're gonna have to solve this problem to understand what a UV complete theory really looks like. So the case that I like to make and the note that I wanted to end on is I would advocate that discovering saturation is comparable to the necessity to discover the Higgs boson. The Higgs boson was a mandatory ingredient for the self-consistency of the Standard Model. We believed it was gonna be there. Thankfully, we found it. But maybe the more interesting scenario was, what if there wasn't a Higgs? If there wasn't a Higgs, we'd be back to square one and we'd have to reinvent the Standard Model. The same is true of saturation. This is a necessary ingredient for QCD to be well defined at all. And if it's not there, it's back to the drawing board and not just for QCD. So with that, thank you guys very much. I think you now have, I should say that this point that I like to make about saturation and the Higgs, not everybody agrees with me on this point. But I think you've got enough information to see the arguments that I've laid out, and you can judge for yourself whether you believe this or not. So thank you very much for your attention and your patience as I've rambled on for more than my allotted time. Enjoy the rest of the program.
So, other questions? Yes, Steve. So,
Yes, ma'am.
First of all, thank you. I've really learned a lot from these lectures.
Absolutely.
So I am not sure I really understand the saturation problem. Is one way of stating it that if you go to lose X, you get like so many gluons that you risk energy. gluons for the energy to get the system? Is that like?
It's not so much an energy conservation problem, although if you're not super careful in how you do your evolution equations, you can run into energy conservation, but that's a theory mistake, not a fundamental aspect of the physics. The issue is just that the more gluons you radiate, the higher probability that you scatter. So as my gluon density increases, I have greater and greater scattering probabilities. And if I just let the gluon density blow up forever, eventually the scattering probability exceeds 100%, and that's not acceptable.
The scattering probability of the electron?
So strictly, it's the scattering probability of the dipole, but the dipole came from the photon. So this would lead to a DIS cross-section that grows too fast with energy. It would lead to a proton-proton cross-section that grows too fast with energy. All QCD cross-sections will scatter hadronically like this at sufficiently high energy. So this is a problem of all high-energy QCD processes. Yes?
How will the EIC help us find gluon saturation?
Ooh, great question. I normally had a slide on this, but I didn't put it in. So back to the EIC comparison. Here we go. Yeah, so this was an important discussion that we had in the negotiations to figure out whether the EIC would be built at JLab or at RIC, because there's a choice there between how high an energy do you need versus the luminosity or other benefits that you might get for other physics programs. And part of the reason for why the EIC eventually went to BNL is because this is the higher energy of the designs. But even so, the highest energy that we can get at the EIC is still lower than the energy at Hera. So part of the argument we had to answer is, if we didn't see saturation at Hera, why the heck do you think you're going to see saturation at the EIC when it has lower energies? And that's fair. The other thing that the EIC has, however, that Hera didn't is ions. And this saturated state doesn't care very much about your initial conditions. If you evolve it long enough, if you evolve it to high enough energies, eventually you reach a state that is independent of your initial condition. Here we go. So for this purpose, I illustrated just like a trivial choice of the initial condition, but I don't lose any sleep over this, because however many partons you start off with, after they radiate 3 or 4 generations of gluons, they start approaching that high density regime all by themselves. So the point is, you can use nuclei to get a head start on saturation. They start off even at lower values of X with higher gluon densities because of their mass number. It's a bit of a back of the envelope formula, but you can say something like your QS squared as a function of X and as a function of mass number scales like A divided by X to the power 1/3. That's highly approximate. The power 1/3 is sort of this saddle point approximation to BK kind of thing. And it's A to the 1/3 mass dependence for the nuclei. But loosely speaking, you can trade off between taking a proton and boosting it an order of magnitude up in energy, which means much more expensive, much more hard to build. Or you could, instead of using a proton, use a heavy nucleus and try to gain a factor there on the density already at your initial conditions. I should also be really clear, though, that realistic estimates for what kind of QS you expect to see at the EIC are not enormously high. Right? If anybody tells you, oh, I'm going to see QS squared of 10 GeV squared at EIC, don't believe it. It's going to be marginal at best at the EIC. We think we can see this starting to get at least greater than about a GeV squared, maybe a couple of GeV squared. Maybe if you put selection cuts on only the ultra-central events, maybe you could push it up a little bit higher. But we're really going to be just pushing into the barest edge of the saturated regime at EIC kinematics, we think. So that's part of why it's going to really take a concerted effort by the community to do a global analysis to find saturation. It's not going to be a smoking gun in a single observable. Yes, sir.
Would blue balls and stuff like that also under like have some sort of point of saturation?
You mean like blue ball scattering?
Yeah, or something.
Yeah,
like
totally.
That existed. How would like what would I guess confine all that?
Do you mean confine in the QCD sense or in the philosophical sense?
In like the QCD sense. Like
Basically, nothing changes about the story. So if I have, I don't know what a glue ball looks like. Maybe a glue ball is this. If I had glue ball scattering at high energies, this guy's going for it, this guy's going for it. The gluons at high S, again, S goes to infinity, T equals constant. The glue balls are going to scatter by gluon exchange. And then as you continue to dial up the energy, the glue balls can also start radiating. It's exactly the same story as you did before. So your initial condition might look different. You might start off with 3 gluons bound together into a glue ball or something. But after you go through a couple of steps of evolution, it's going to start looking like 100 gluons, 1,000 gluons, and it's going to approach saturation in exactly the same way. Does that answer your question, or did I miss the point?
A little bit. I guess it was more along the lines of like, what would set the point for that level of like how many gluons can exist in level of saturation?
Okay, it's a little bit of a tricky question because it's not just the number of gluons, it's the number of gluons as a function of momentum. So let me illustrate. Here we go. So what I said before is that in the dilute region, so say down here where the momentum is small, these guys are growing exponentially fast. But in regions where the density is high, this has slowed down. So it's not just that the number of gluons is growing, it's growing differently in different regions of momentum space. So your initial condition will tell you, like, what do I start off with down here? And then in all of those cases, the dilute regions will start to grow exponentially fast and such. So it's not just a question of how many gluons, it's also a question of how they're distributing momentum space.
Okay, so it would, like depend on the like initial momentum.
That's right.
Okay.
But eventually, if you evolve it long enough, there's whatever the structure was down here is going to start turning into this peak, and it's going to start moving out this way. And once that starts to form, you have this universal behavior. You can even write it as a formal attractor for the evolution. Yes, sir.
So what if there are quadruples of the can you still use BK or Higinbotham is on the
You could probably do 1/NC corrections to BK.
I know that if you do two long production.
Yeah. It's not just dipoles. Yeah.
Now larger limit quadruples don't.
Yeah. Yeah, it's only for the like single inclusive observables like this that dipoles are sufficient. Yeah, to do more differential observables, you need more complicated multiple operators. Yeah, absolutely. Yes, sir.
So, like as you said, we do not know whether in PA or AA or even high multiplicity PP that QGP formation does not happen. And then EIC gives us a chance to form even smaller collision systems.
Yes.
But then what probe do we use to find at which system size that QGP is not formed in EIC?
Well, I would go to ultraperipheral collisions right now as my cleanest way of looking at this. But if we still see V2 does not turn off in the smallest hadronic systems that we could get, then I would go to this and I would look at it as a function of Q squared. Ideally, I would expect to see, let's say, V22 as a function of Q squared in DIS. I would expect to see the larger Q squared, the smaller the system. So I would expect to see something like this. And if I still see sizable V2 at this value of Q squared, then I would take a bin with a higher value of Q squared and I would look for where it disappears. So if there is, I don't know, a sudden switch off of the QGP, then I don't know, maybe there's a magic Q squared for the QGP where you have V2 and then suddenly it's 0. I have no idea what that might look like. But if we're looking for a turn off of signatures of the QGP, what I would say is as a function of system size, that would translate to turning off of the signals as a function of Q squared. And you have the ability to go to as high a Q squared as you want at the EIC, whereas you're limited by proton, the size of the proton or the size of the pion system just by the stable hadrons themselves.
Okay. I think we are in time. So I will stop here. I have just a curiosity. Just,
sure.
So by looking at nature, it could be that neutron star has color saturation.
Could be.
It's just a curiosity. So do you think that is a possible place where this thing could happen?
Neutron stars aren't really where my mind goes. I would be much more interested in ultra high energy cosmic rays.
Okay.
So if it turns out that the EIC is not low enough X to find gluon saturation, if the LHC is even not low enough X to find gluon saturation, what other choice do we have? Earth is being bombarded by space from space by ultra high energy cosmic rays, far higher in energy than anything we can produce on Earth. So it's harder. You don't have a hermetic detector for those. But if you need higher energies, that's about the only thing that I can think of.
Okay, I think we can stop here. So thank you again, Matt, for all the lectures. I think we can reconvene in 10 minutes, that we are a bit late, but we need a break. We need a break, yeah. And for that, I mean, we saw the theory, and next seminar will be on experiment, right? Yeah, I see.
say something? Okay, now I can.
Okay, perfect. Okay, so we can start. This is our first topical seminar of this HUGS, and we have here with us Doug that will present some motivation for EIC. He's a senior scientist here at JLab, and they are all yours.
Awesome, thank you so much. And I'm gonna get it started, give a high level picture, give a little bit of history, the timeline, and then there will be the real talk from Yulia, who's sitting in the back, and she's gonna go into the details of the detector. She can answer all the hard questions. I'm up here to have fun. Right. I don't know which. All right. I don't know which hand. All right. Here we go. All right. I'm a Jefferson Lab employee. I've been a Jefferson Lab employee for 20 years. I showed up here 21 years ago as an MIT postdoc, and I just never, ever left. And now they can't figure out how to get rid of me. I love Jefferson Lab. I love the physics we do, and I still love the physics we do. But I'm giving the EIC talk. I'm going to start off by saying a little bit about JLab physics, because there's still all kinds of cool stuff we can do here. There's over a decade of physics to do here with the 12 GeV beams. There's lots of new ideas. And for those of you who will be around on July 11th is when the next program advisory committee meeting is. This is where the scientists go, and maybe even some of your advisors, they have an experimental idea, they want to run it in this lab, you have to defend it in front of an advisory committee. They are tough, and they're tough on the experiments. The idea isn't sound, the physics isn't sound, they kick you out. On the other hand, that's where the experiments we do come from. So the ones that make it through, it's usually about a third progress. That's what can possibly get scheduled. Know that those that progress, even some of those never get done. And there's lots of new ideas, and hopefully you'll hear about some of these during the HUGS lectures. Positrons instead of electrons in Jefferson Lab is a possibility. Reverse the polarity of the dipoles, set up the injector differently. There's a brand new topical collection on those ideas. There are already some approved experiments from recent packs. So this is 2 years ago, pack 48. And there are now even really cool ideas about increasing Jefferson Lab's energy without increasing our footprint. There are some really amazing nonlinear accelerator optics makes that possible. All right, so that's JLab. Why is EIC interesting, and what questions will it address? All right. These are not my answers to one of the key scientific questions of the Electron-Ion Collider. This is from a National Academy of Science report. On my slides, the link is here. You have to click around to say, give me a free copy, but you can get the report for free, you don't have to pay. So it goes into great detail why the Electron-Ion Collider is interesting. And these are the big questions. How do nuclei properties of mass and spin emerge? Are protons inside the nucleus distributed in momentum and position space? Look at color charge, jets interacting with the nuclear medium. How's the dense nuclear environment affect quarks and gluons? Now, some of these questions are very similar to questions we ask at Jefferson Lab, but we ask in different kinematic range. So Electron-Ion Collider, you're often concerned with C quarks. So if you want to imagine proton, you want to be naive about it, right? I think proton, I got 2 up quarks and down. As I zoom in my microscope, look at very low Bjorkane X, I start to see the C quark, anti-quark pairs, gluons. It gets incredibly complicated. So Jefferson Lab tends to push to the high X, where that simple-minded picture, the valence quark picture, comes into play. And EIC is going the other way, and they're looking where the low X, where the C quarks and gluons apparently really matter. And to put that into a kinematic chart, so here I've taken the Bjorkane X variable. I'm an experimentalist. Since I measure everything, this is easy peasy. It's a form of momentum transfer squared. 5/2, mass on my target, energy of the beam minus the energy coming out. That's it. Elastic scattering, so I'm coming out with my beam, hit a proton, proton stays intact, doesn't excite. That's a Bjorkane X of 1. If I knock the living daylights out of it, make all kinds of stuff coming out, I'm down here at low X. And also probing the C again. So valence quark region, C quark region. And there's probably one thing that I wish I had time to change. Jefferson Lab, of course, does not stop at a Q squared of 1. I decided to cut it off 1. We keep going. Someone put a deep elastic cut there, and then didn't do it for the other labs. Anyway, when you glance at this, you might go, oh, wow, look, EIC can pretty much do everything. Yes and no. Sure, if I just want a few events, it does everything. EIC can go to X near 1, and the Q squared is several thousand. Great. There's no rate. I like to do experiments that get done in some reasonable amount of time. So the one dimension that's not shown on this plot that you can have come out would be luminosity. And experiments in this region at high X tend to be very hungry for luminosity. So for example, your experiment at Hall C coming up, doing pion LC experiment, they want the highest beam energies we can deliver. They want the highest currents we can deliver. They want it on thick targets. They're going to luminosity is 10 to the 38, 10 to the 39. This blows what EIC could ever do away. On the other hand, Jefferson Lab can't reach into these kinetics. So each of these facilities has a region where they do really well. Physics, they can do really well. And as you can see on this plot, there's nothing out here yet. So this is where the EIC is going to absolutely shine. And again, just to get back to that luminosity, so Hall C 10 to 38, 39, the best EIC does at their optimized center of mass energy, this is their 10 to the 34. One thing to just stick in the back of your head, because you will hear people talk about EIC luminosities, it's not a flat line. It's not like they hit one luminosity, it's true overall center of mass energies. There is an optimal where they've tuned this machine up, it's designed for a particular center of mass energy. It shall be able to have a dynamic range, but you will roll off the max. This can, of course, be improved as a function of time with more money, effort, but the baseline will look something like this.
Yeah.
I've messed up the quick.
No. This because of me. So.
Ooh, all right. All right. Now, these should look incredibly familiar to all of you. So Electron-Ion Collider is, of course, a collider. So beam of protons, beam of electrons, or beam of ions, beam of electrons collide. The Feynman diagrams for the inclusive deep inelastic scattering, whether I'm doing that for the AIC or I'm doing it for Jefferson Lab, it's the same Feynman diagram. And I can always boost to a frame of reference where the ion's at rest. And this actually explains why the EIC can't be done here with fixed target. So I'll leave it to you as an exercise. So right now we have an 11 GeV beam and I can put that on a proton target or a carbon target or a lead target. But the target's fixed and beam comes in. If I wanted to get to the same kinematics that the EIC does with a fixed target, I need TeVs of electron beam energy. It'd be insane. The right way to do it, and the way we are doing it, is instead of trying to take just the electron energy and raise it up, if we want to get to those lower kinematics, accelerate the proton beam, accelerate your target into it. But from a theory point of view, right, I can always do the boost. Physics is the Lorentz invariant, right? So I get back to my Feynman diagram. So proton in, electron in, exchange virtual photon, have my deep inelastic scattering, detect only the electron. I can do semi-inclusive deep inelastic scattering, detect the electron, detect the meson, for example, and then fully exclusive reactions, detecting electron, other particles, meson, gamma, and proton, and variations thereof. These are the main Feynman diagrams of the EIC. It is by no means exhaustive. You can go on forever, just like you can here. Many experiments we do, just some of the main ones. And these are a lot of these diagrams cover a lot of the questions that we'd like to address for driving the EIC, but certainly about the entire program. All right. So what I wanted to do today is give you a little bit of history. It's not that long ago, so an amazing amount of progress has happened on EIC just over the last few years. And amazingly enough, COVID did not slow this down. We were kind of lucky just as things were progressing. So October 2019, there were two concepts, or two laboratories say fighting, or fighting is too rough a word. Competing. Nicely. Yeah, fighting for Electron-Ion Collider. One was Brookhaven. Brookhaven has an ion machine. They are right now. They're an ion collider. They're getting ready to upgrade IP8 here. This will have the Super Phoenix detector. That is getting ready as we speak right now. They're building it up and getting ready to slide it in to the experimental hall. Their idea for an upgrade was to build an electron source. They were going to add an electron ring collide. Brookhaven's idea. Jefferson Lab's idea. We have an electron beam. We'll build this cool figure-8 ion machine. We'll feed it from CDAP, so we have the electrons. We'll have this new custom design for the ions. Both machines had advantages. The biggest advantage of the Brookhaven machine is on a very large piece of property. It allows them to easily get to very high energies. Jefferson Lab's very constrained in where we fit. We're in a city. Brookhaven's way out on Long Island. On the other hand, this figure-8 design was actually quite clever for one thing, and that was polarization. It's really easy to store not only polarized protons, but polarized deuterons in the figure-8 design. This is a naturally spin-preserving design. You can do the same thing with a circular beam. It costs a lot of money. You'll need something called spin rotators, and to do the deuteron in particular, it's very challenging. So this one was more energy reach in my mind. This one was more polarization reach. But both designs could do the physics as outlined in that National Academy of Science report. But I couldn't move the Jefferson Lab to Brookhaven or Brookhaven to Jefferson Lab because all I really need to do is collide the electron beam from here with the hadron beam from there. We're way too far apart. So I need to pick one. All right. And this should be no shock to anyone. This was chosen as the design. And this is where life got interesting, because historically, when labs have kind of had that, fight it out, you get the winner and the loser, right? Winner goes on, loser goes home. That didn't happen. And it's actually a much nicer model what did happen. So critical decision 0. So these CD zeros, this is Department of Energy jargon. You can think of it as milestones. And critical decision 0 is the first one. It's a statement of need. It's when the US Department of Energy makes a statement that the United States needs Electron-Ion Collider to stay preeminent in the field of nuclear physics. And then they point to the National Academy of Science report to show the physics it will be able to do. And it was on this date they down selected. Well, this is the date it was selected. This is the date we found out about what they had decided on the Brookhaven design. All right. And many of us had worked hard, myself, Yulia, many others. So we were disappointed. That's absolutely natural human reaction. Right? You work hard, you don't win. Right? You're not happy. All right, he's happy. Most of us aren't happy. Tim Hallman came here, actually came to talk to us. And he was like, guys, girls, look, this is your physics. So right now, Jefferson Lab does electron scattering. Those Feynman diagrams are what we're doing. It's what you're learning about. It's not what they're doing at Brookhaven right now. They're doing heavy ion collisions. He's like, guys, keep developing the intellectual ownership of the physics. Keep working. And this idea of, instead of, let's say, throwing up your arms, giving up, and instead of going, no, we want to do this physics. We are excited about the physics. I don't care if it's built here or there. I want to do this physics. And it really resonated. And very quickly, disappointment turned into, let's work together, really work together as a team. And that has actually become formalized. And again, this isn't what usually happens, but it's a great model. So Brookhaven and Jefferson Lab have signed back in May of 2020 a partnership agreement.
Sorry, Doug. Your microphone, turn it off. Something. Yeah. I don't know, maybe the bottom.
All right. What can I use? Wait, is it?
Maybe just press the blue button.
No, I have no battery.
Yeah, the second one.
I'll keep going. We'll change it. All right, are we back? Okay. So May 7, 2020 partnership agreement. And this was great. And this is the way you kind of like science to always go, right? We develop ideas, maybe we have two different ideas, but we're all trying to get the same physics goal. There's a review, one is selected, but instead of one group of scientists going, well, I can get my way. Instead, take a breather and come back together. It just, I hope that this model continues. I think it's fantastic. And it has been a great partnership. It brings the ideas of both groups together and more scientists thinking about a problem, right? Just at a fundamental level better. I'm not gonna spend much time on this. I just wanted to show a formal organizational chart. This has many Jefferson Lab names. Rolf Entz, who used to be the head of physics division, he's now the associate project director, detector for EIC, and there are many JLab people throughout the EIC project. So really integrated into the project formally, very unique. All right, so I want to give you a visualization of what this upgrade will look like. Hopefully this will work. So this is schematically what Brookhaven is like right now. So an ion injector, AGS, taking ions, a little switch yard, so they can send the ion beams clockwise, counterclockwise into a storage ring and bring it to two interaction points. This is IP6. This IP6 notation continues. It will continue into the IP. It's just a clock location, so it's 6 o'clock, it's IP6. This is where the star detector is currently located. And IP8 is where the SVX detector is going in. So two interaction points. That's what they have right now. And this is what likely coming. Right? And I say likely, cooling is still one of the open issues, but you keep the ion complex piece mostly the same. You can see one of the switch yard pieces is removed. And I build, oddly enough, 2 electron injectors. One of them I'll call my clean one. It's the one that's going to produce polarized electrons from a source. It's the same technology we have here at Jefferson Lab. So you use polarized light on strained gallium arsenide, and I can pull off polarized electrons. I'll use those for the collision. But there's a second source of electrons here where they're going to have high current that they want to use for cooling. And this is just a cute idea, even just classically, you can think of this. You have a beam of protons. You imagine classical protons in an ensemble traveling around in a circle. I want them to collide with an electron beam. So I have a nice point like electron beam and some mushy ensemble of protons. I'm not going to hit very many of them if they're all spread out. I'd like them to be in a nice tight beam, a cooled beam. And one of the ways you can do that cooling, it's classical. I can put the beam of a beam of electrons beside it so that the protons, which are thermally moving, bump the electrons and they will lose some momentum. So I keep refeeding this very light electrons, a half an MeV in mass, a very heavy proton, and I can cool it. I can cool the proton beam. That's one of the ideas. And the reason cooling is something we get excited about as scientists. We'd like to do our experiment in a reasonable amount of time. Is cooling means luminosity. And I can't cool, and those luminosity numbers 10 to the 34 start coming down to 33. And just saying numbers like that means nothing. So let's put it in terms we understand as human. An experiment that would take 1 year at luminosity 10 to 34 takes 10 years at 33. Right? Nobody wants to stay in graduate school, get their data for 10 years. I want to get my data in 1 year, analyze and get out, right? So it makes a huge difference in what science reach you can have with luminosity. And that's why people get so excited about pushing on luminosity, make sure the luminosity stays up. When it goes down low enough, I'm not going to do any of the cool stuff. All right. I wanted to show this just because it was done by a Jefferson Lab Sully student. This is now 2 years ago. But not only do they do the cooling to get the luminosity up, they do something called grabbing the beam. And I learned from Ollie that grabbing is actually a term used in helicopters. This is when you rotate your helicopter. So you're moving forward, but you rotate the helicopter, you move at an angle. You're moving like a crab. So instead of moving like this, rotate. So this is idealized, but it's an idea of I've got elliptical ion beam interacting with elliptical electron beam. And what she's done here is showing you what the overlap. This is just a two-dimensional picture. It's a little bit of a cartoon, but still, you can see you never perfectly overlap. No kidding. What you can do, and this is what is being done, is add a so-called crab cavity. Take that bunch, perturb it so it starts wiggling. So there are a lot of quadrupole magnets not shown along here that keep the beam in its nice orbit. But beam bunch will start to oscillate, and you time it such that the electron and ion bunches perfectly overlap. And even in my little cartoon, getting that perfect overlap immediately gets me another factor of 2 in luminosity. So instead of 1 year, I can do it in 6 months. Cool, graduate faster. But every little thing about getting luminosity up is important because it really all has to come together. That's what lets us hit those high luminosity numbers. All right. The other thing that's very different doing electron-ion colliding or any of the collider experiments compared to Jefferson Lab is the kinematics. Again, I can always do the Lorentz transformations or just keep things in Lorentz invariant quantities like Q squared. We're all talking about the same thing. But as experimentalists, I'm usually thinking in the lab frame. So I'm thinking in this frame where I have a beam of electrons going one way. I've got my proton or ion beam going in the opposite direction. I have a collision point, and then I build a detector up around that. Now this is extremely cartoony. So we've got a central detector region as box. We've got 2 end caps, one to detect the scattered electron end cap, one to detect scattered hadron. Because remember, these particles are coming in relativistic to each other. They will collide, but most of the time they'll just graze each other, right? That's why these end caps are so important. And the new terminology to get used to is the pseudo-rapidity. So for electron scattering in a fixed target facility, we always just think in terms of the angle of the scattered electron. So whether you're in hall A, B, or C, right? Electron beam comes in, I know the scattering angle either in the spectrometer or in class. It's easy peasy, it's just an angle. Here, it's more useful to talk in terms of pseudo-rapidity. If I have a heavy ion collider or a proton-proton collider, this is where most of the events go. Imagine I had a proton on a proton, they have the same momentum, same energy. They come in, they'll just pancake on each other. Everything will come out at 0 rapidity, most things. Anyway, here I've just listed how rapidity maps to angle. So angle of 0 degrees is a rapidity of infinity, if anyone cares. But it's just a new term. And if you're like me, this is algebra. It's just something to get used to. All right. And this is a cartoon. This dates back to something called the Yellow Report, which I'll mention near the end of my talk, of what the electron-ion collider is expected to look like. And it has morphed, and it's continuing to morph. You'll see a few different images of ideas that have come about as a function of time. But though it keeps morphing, it gets refined. A lot of it continues to stay the same. And a lot of the detector technologies in this device are the same as what we have here, though some are different. Number of calorimeters, these tend to be leaded glass blocks, something called side glass. These are materials to stop and cause electromagnetic showers. My favorite detector type, the Trenkov detectors. So these are your detectors where the particle is going faster than the speed of light in the material. I always thought that was cool, right? It can't go faster than the speed of light in the vacuum, but these particles can go faster than light goes in certain materials. So it can be a gas, it can be aerogel. We have a number of different types of that detector. Dirk is a Trenkov detector. There's also a dual rich now, which is just labeled rich. There's also tracking detectors. So they'll have wire chambers, gems, silicon, all brought together. And it's not so different in scale. If you've walked down the hall D and looked at their detector, it's actually similar in scale. This is Natalie. I think she's running for the user group, as a matter of fact. Anyway, this is a cartoon again of a possible electron-ion collider detector being pulled out of the hall. And one of the fun things working at a facility that's already built, you have to deal with things that already exist, like the door. So this is IP6. And this is a headache. So the door isn't really as big as you'd like it to be. If you were building this from scratch, you would build a bigger door. Civil construction is always expensive. I don't care if you're digging a hole or building a new building, you try to avoid it if you can. And the way we avoided it is we made it so these end caps, so the electromagnetic hadron end caps can come off, and the main part of the detector can slide out to work on it. And this is just one scheme how this can work. This picture is from here in test lab. You can go take the same shot if you want. This is the Clio magnet. This is the magnet that's planned to be used, or the iron yoke for the magnet for solid. It's the same size. So whether I'm talking about the solid magnet, the magnet that's in hall D, the magnet that's inside the EIC detector, they're very similar in size. They can be a little bit bigger and smaller, but the scale, this kind of human scale, a radius of a student, is roughly, just to give you guys a feeling, because when you look at these cartoons, at least for me, it's very difficult to figure out what the heck I'm looking at. It's a desktop. So, radius of a human. Now, for most scientists, I think they really like the physics of the central detector. I guess I'm a bit of a contrarian, so I actually like the physics you can do far away from that central detector. This is a diagram showing something called the far forward region. So if you imagine the scattering electron-ion colliding, oftentimes the ions will just continue almost down the pipe, that pseudo-rapidity of infinity, the 0-degree scattering. And for me, a lot of my physics, so the short-range correlation physics, there's pion production physics, gets done in this region. And this is where it gets really cool and novel, because I now have detectors. So instead of just all the detectors around the interaction point at the central detector, so this is the central detector, I start having little detectors along the beam line, so-called B0. So this is a dipole magnet detector inside the magnet. Tracking detectors located near the beam, Roman pots inside the beam line. These are silicon detectors in the pipe. And then a 0-degree calorimeter. So this is a calorimeter that I just go from 0 degrees. So this is roughly 50 meters back to the target. So a neutron that isn't going to get deflected by any of these magnets can end up on that detector. Also gammas. All kinds of neat equipment. And I just want to give one example, and there are a vast number of examples. I just want to give one. And this is one. This was published by a number of researchers. These are some of the Jefferson Lab EIC fellows here. Let's see, Jackson's still here. Zien is here now as our postdoc ISCR fellow.
And she will lecture next week.
Oh, that's right, she's your lecturer. So if you have questions about this slide, you can ask her. So one of the cute ideas, and this is a novel idea, this is not one of the ideas that drove the initial design of the detector, but what makes any facility like Jefferson Lab or the EIC CERN, any of them really rich, isn't just that initial set of physics ideas. If the only things I can do are the initial set of physics ideas, something's probably wrong, right? I mean, what's cool is when you keep thinking or you refine the ideas or come up with something just completely different. And this is in the pretty completely different category. And this was doing tagging with polarized helium-3. So helium-3 is one of our go-to targets here at Jefferson Lab. So if you have the store by balloon, helium-4, 2 protons, 2 neutrons. A little bit of the helium in the balloon will also be helium-3. So it's missing a neutron. Chemically, it's the same, all the same properties as helium. Medically, it's kind of cool because I can polarize helium-3. I can polarize the neutron. So we've got 2 protons, they'll go spin against each other. And the spin of helium-3 will be carried mostly by a neutron. We know this from the magnetic moment. Magnetic moment of neutron and helium-3 are very close to each other. As the first hint. Anyway, most of us have sucked on a helium balloon. Makes your voice squeaky. It's an inert gas. Fantastic for medicine. If you breathe in helium-4, it makes your voice squeaky, but who cares? If I breathe in polarized helium-3, you can all of a sudden do absolutely gorgeous imaging of the lungs in an MRI machine. MRI machine, magnetic resonance imaging. It's really nuclear magnetic resonance imaging. And having the polarized helium-3 in the lungs all of a sudden gives gorgeous images. The problem with the technique at the moment isn't the ideas behind it, it's the cost of helium-3, which is prohibitively expensive for industrial use at the moment. And to be honest, you don't want that price to come down. Does anyone know why? You know where helium-3 mostly came from? From the arms race. All right, also tritium. All right, so what was the novel idea Zien and others had? When we do deep inelastic scattering on helium-3, this experiment we just did in Hall C, so electron beam in, we scatter on the polarized helium-3, I measure the scattered electron, I'm in deep inelastic scattering kinematics. Awesome, but I can't control what I'm hitting. So even in a naive picture, I've got 2 protons sitting there. So I'm going to scatter mostly on protons, not neutrons. And I use polarized helium-3 because I want to study neutron physics. I know the protons already from doing proton scattering. I have a polarized proton target. So I have to do a subtraction. So I take the experimental data, inclusive electron scattering on polarized helium-3, and I correct for the proton. Yuck. Could I do it better? At the Electron-Ion Collider, what you can do is tag both protons. So if I truly hit the neutron, so just think naively again, so I've got helium-3, I've got this neutron, I've got 2 protons. I'd like to be hitting the neutron. If I do, I've done deep inelastic scattering the neutron, what's left over is 2 protons. Since this is a collider, they're just going to continue down the beam pipe. They're going to go right down that far forward region, and you can detect them in the Roman pods. So I can detect 2 protons going. All of a sudden, I know I hit the neutron, and everything gets so much easier. So what's shown here is the asymmetry I get when I do an experiment like A1, where I want to be measuring A1N, A1 neutron. This is what I really get in the lab when I do that inclusive experiment. By doing the tagging, I will get what I really want to start with, or much, much closer anyway. All right. And this is just one example of science we can do better with Electron-Ion Collider, making use of the unique kinematics and geometry of the far forward region compared to what we have here now. This is just another paper from Jefferson Lab. One thing that's I'm finding peculiar is it's relatively easy to publish papers where you do studies as opposed to real experiments. Anyway, okay, as of October 2021, this is the schedule for the Electron-Ion Collider. This changes, it's going to change again. Any kind of schedule for a project, whether it's the carriers that we build here in Newport News. Y'all do know we build carriers. I'm not kidding you. That's what Newport News is, a shipbuilding town, has been for decades and decades, back to World War I, II, before. So you can drive down to and see the carriers in construction. You can also see the USS Enterprise being torn apart as it's decommissioned. Okay, but whatever the project is, whether it's the aircraft carrier or the Electron-Ion Collider, how long it takes you to get it done depends on the amount of funding you get. Right? And we haven't gotten the amount of funding we wanted, which is what's pushing things back. But nevertheless, it moves forward. So the first step is this so-called critical decision 0, the statement of need from the Department of Energy. We've already passed the CD1 milestone, working on CD2, 3. Many ways, these are steps along the way. The one that's really important in all these projects, you hit critical decision 3. Why is that the really important one? That's one where big money is flowing. This is where when you got to this point, you have fixed your design. I know exactly what I want to build, and I'm ready to go. And you can also see on the timeline, there's a big gap between 3 and 4. This is when you're doing the construction, the installation. So what needs to happen, and what needs to be happening right now, I need to be doing the design. I need to be taking the detector ideas that the scientists have come up with. We need to start solidifying what we want to do. It doesn't have to be perfect yet, but I need to come up with a baseline. I need to come up with a rough cost, then do final design so we can start construction. So this has CD3. This is in fiscal years. So fiscal years in the United States start in October. So this is the October of 2025. So you're pretty close. And it's probably shifting out about 6 months. And it's simply because we didn't get the funding level we had hoped for the project. So if you don't get your funding, it slips. Nevertheless, you can get pretty good rough idea. So in 2030, the Electron-Ion Collider should be completed. It should be starting to run. We should have one detector at one of the IPs. That's what's included in the project. So anytime people start talking project, they get very formal. They start talking about these critical decisions and what's in the baseline, what's in that project. And as proposed, there's only one detector. Now, Brookhaven has 2 natural interaction regions, one at IP6 and one at IP8. And what is included in the budget is to make sure to make no decision that would preclude a second detector. What's not yet obtained, a CD0, is a second detector. Nevertheless, people have started to show a timeline when it would be possible to have a second detector at Electron-Ion Collider. So this is something that would follow behind roughly 4 or 5 years from the first detector. And this is very fuzzy. So this is proceeding, and everything up to today is where we are. We're really into this design phase. And there are many aspects. These are aspects you can go look at. One is the EIC yellow report. This is a horrifically long document, 902 pages. I managed to get it to upload to the archive and compile. That's my greatest success. So if you want, you can check out my LaTeX. It is quite a slog if you want to read all 902 pages. On the other hand, what is really nice, and I think all of you should look at, is the executive summary. So there's a summary of this 902 pages, roughly 10, 20 pages long, beautifully polished, carefully worded. And the other sections are phenomenal for reference. You want to look up a particular physics topic, you can do it at EIC. You can look in the physics detectors, use it like a encyclopedia reference book. Anyway, that's how I look at it. That's one resource. Okay. Now I'm almost up to today. So what happened over the last year? So we went from kind of a generic idea. So this happened pretty much all during COVID lockdown. Work on refining the ideas, justifying the physics case, refining it, I should say, and really fleshing out what I wanted in detectors. What the detectors need to be able to do to get the science done. That was on the yellow report. Now make it even more concrete. Collaborations formed, came up with ideas. There are 3 proposals. This was done over the last year. one called Athena, a Core, Eche. These are SketchUp models of all three designs. At a glance, they're all similar. They're all solenoidal magnets. They did have different characteristics. The Athena one, for example, could go to a 3 Tesla magnetic field. The Eche one is reusing the same magnet that's being used in S-Phoenix. It's the bar magnet. It can only go to 1.5 Tesla magnetic field. And the compact design one was basically an idea for a second detector, though they also proposed themselves that they could be the first detector. So 3 ideas came in. They were all reviewed for cost, risk. Could they get the science done? I think the committee was very positive on either the Eche group or Athena group could get the science done, had a very strong collaboration. But again, you're now one of these points where a committee makes decisions. They decided to go with the Eche. This is the 1.5 Tesla reuse a magnet. Of course, reusing makes things a little cheaper. It was also a little bit smaller, which is also cheaper. So this is March 22nd. So now we had another one of these winner-loser situations. But again, okay, first, okay, you had winners, losers, feel happy, sad. Human reaction, we get over it. And we're now coming, we are literally right now coming back together as a community and going, okay, baseline has been decided. So some basic parameters. I know now the size of the magnet and the field of the magnet, I have the basic layout. And now we iterate again because I don't want to just stop. I'm not going, I'm building this. I want to take, or we all want to take the best ideas from all three and combine them into this baseline. So you think of it as iterative and yeah, go ahead.
What were the groups that were proposing each model?
What do you mean?
Like each of the detector concepts, what were the groups that were proposing?
Okay. So there's a mishmash of scientists in each group, and there was a lot of overlaps. A lot of people worked on multiple ones. The Athena group had a lot of members of the STAR community, so the IP6 community at Brookhaven, and a good fraction of Jefferson Lab people scattered from different halls. Eche was more the Phoenix community, the IP8. They were using the bar magnet. It's natural why that group was interested more in this design, and again, had a spattering of Jefferson Lab people. The core one, this was more driven by Old Dominion University in Stony Brook. It did not have as large a collaboration. The one thing that's amazing when I say STAR and Phoenix, this is a collaboration bigger than class. So when those groups show up, they're two huge teams of people. So this one did not have as many, let's say, scientists involved. That's why I think from the committee, if you just read the report, you make your own decisions, but they're pretty much focused on the big two, the Athena collaboration and the Eche collaboration.
Sorry, Doug.
Yeah.
You have still 5 minutes.
All right, perfect. All right. And from a historical point of view, I've brought you up to today. This is what we're doing now. We've down selected. We're not done. We're going to refine. We're going to take the best ideas from all the teams. And we are literally just getting over this first human reaction of winners, losers, and it happened again, but it is always nice to see people come back together. In fact, during the yellow report, we've all been working together in I thought, a really great team. And when this call for proposals came out and we broke into separate teams, I didn't actually like it. I actually preferred when we were kind of all together. But anyway, it was exercise that needed to be done. We needed to just really dig in deep. Do I need the 1.5 magnet or do I need to build the 3 Tesla? Let's do the science. Let's have a review committee decide independently what do they think? Is it good enough or not? That's what's happening. All right. So just some really quick numbers. So it's roughly 1,300 collaborators already working on EIC. That's just slightly under the Jefferson Lab user community number. These are just ones that are formally registered on the EIC user group page. Those are ones that are captured. Just really quick, a couple things to point out to you all. So here at Derson Lab, we have something called EIC Center Fellowships. There are 3 for postdoctoral scientists and 3 for PhD students. It's a bit of funding for both to allow the advisor to have the student or postdoc work on EIC science. The call for that is out. So if any of you all are really enthusiastic about EIC science, I strongly suggest you talk to your advisor. From my point of view, it works best when there's a synergy between what you're doing right now for your thesis and EIC. And there's amazing overlaps, whether it's deeply inelastic scattering, structure functions, goes on. In the polarized helium 3, that experiment is proposed for class 12, can also be done EIC. All right, just flash up, these are our current fellows. And final thing I want to mention has been very beneficial is the detector testing program. So Jefferson Lab is not known as a detector testing facility by any means, but our users, our professors have been doing detector testing on the side for as long as I can remember. So for 20+ years, people have been putting little detectors near the beam, off to the side. All the experimental halls will run a few cables, we'll test the detectors. What's happened recently is it's begun to get a little more formal. In particular, in experimental hall D, behind their electron positron tagger is a beautiful location for doing testing. Yulia's done many tests there. We've done modular ridge testing there, gem testing there. So while this kind of in its infancy, it's clear that detector testing at Jefferson Lab is something that's going to not only continue, I think it's going to grow a little more formal over the years. So just to wrap this up, so even though Jefferson Lab didn't win the site, we're not building Electron-Ion Collider next door, we have a really strong commitment to the IC. The science is science many of us here really love and we're really excited about. So we're going to keep it going, keep pushing. We're heavily involved. And for any of you who are interested, on Fridays at 9:30, we have a weekly AIC meeting. Everyone is welcome to come listen in. Topics are all over the place. We will do accelerator science, nuclear physics, nuclear theory, detectors, different detector technologies. So you can just look in the announcement if you're interested. If it looks like something you want to come or listen to, you're absolutely welcome. These fellowships are open. And I'd be remiss if I didn't point out 2 really neat opportunities for students. There's 2 very heavily subsidized workshops coming up. One at Stony Brook, there's an EIC Center Early Career Workshop. This has got a lot of financial support from JLab and Brookhaven, others. And also there's the Photonuclear Gordon Conference. This one also has a lot of funding available for students. And what's kind of really cute about both of these is these early career parts. So for EIC Early Career Workshop or Careers and Frontiers, it's organized by the students and postdocs. So these are the senior scientists coming up with the agenda. This is students and postdocs coming up with the agenda. Opportunity for younger people to talk in front of your peers. And I will leave it there. Thank you.
Questions, comments?
So how do you cool electron? You add electron to cool the proton beam.
So I was cooling the proton beam. Let's see. So Yulia, correct me if I'm wrong, but I don't believe there's any need to cool the electron beam. It's just like here at Jefferson Lab. So the electron beam off the photocathode into the machine, there is no cooling because the beam is gorgeous. I mean, it's hair-sized, gorgeous to begin with. So I don't need to cool it. It's not a spread out beam. It doesn't have a lot of transverse momentum. So the problem with my hadron beam is it's not the forward momentum that's problematic, it's your transverse. So think of it as perpendicular momentum to the direction of motion, and my beam bucket is oscillating about that. Sort of, that's why it's like thermodynamics. It's literally oscillating, I need to cool it. Electron beam, on the other hand, No, we need to cool the hadron beam. Could you cool an electron beam? Yes. But that's not our problem at the moment. Yeah.
So if Jefferson Lab were to have like received the EIC or received funding or was chosen, what would happen to physics at the other halls?
Oh, wow. Someone was actually pointing this out the other day. Oh, come on. All the way. So I had this question asked me in a different way, which was, so was Jefferson Lab lucky not to get awarded the EIC? And in a way, the answer is yes. So there's positives and negatives to everything. Let me start with the negative at Brookhaven. They have been awarded the Electron-Ion Collider. In order to get the award, they promised to redirect program funds to EIC. This means they're going away from something. They're going away from STAR, and they're going away from S-Phoenix. S-Phoenix is not going to be able to run as long as many of us had hoped. And it's to ensure that the EIC project moves along and the promised funds have to move. So that program would end early. At Jefferson Lab, if we had gotten the collider, it would be similar. We'd have to start putting our resources mostly into the collider. Yes, we could continue to run the 12 DV program in the halls. Nothing precludes it, but it would be much, much slower than it is now. As things look right now, Jefferson Lab's going to keep rocking on. We'll do as many experiments as we can every year. In just a few more years, Brookhaven will stop the machine so they can do the installation of detector 1. And there, for many years, it'll be off. And during that time, we'll be, say, the only game in town. So we'll be doing a lot of science. So you can think of it from 2025 to 2030. This is where people will be coming. And this is why I really like the EIC Fellow program, right? Because what I really want to do, the science overlaps, a lot of the physics. So deeply virtual confidence scattering comes to mind as one. But you can do those experiments, and we will be doing them in experimental hall B, for example. In different kinematics, you'll be doing those experiments at the Electron-Ion Collider. So absolutely need to keep, let's say, the pipeline of students engaged, trained, right? Because I can imagine the student from here will be doing the postdoc at EIC, depending on the timing. In fact, some of you in this room, I suspect that'll be exactly the case. Yeah.
Why is it wiggly? Why is it a wiggly circle, not a circle?
Ooh, you have a great technical answer, Yulia, for the. So no. So, and you're absolutely right. It's nice you noticed. So the Brookhaven machine is not circular at all as you get into the details. It literally has all kinds of, let's say, macroscopic detail as the beam wiggles around. The entire history of all the optics. So a lot of this comes back to the ion machine, which I was not involved with in any way of design. But you just think about the practical matter of putting in the magnets and the optics and where everything goes. Yeah, you end up with a circle. A curiosity about the electron-ion machine that's not evident in these pictures at all. In order to fit it in, so okay, you won. Now let's really start drawing this up. And you try to put the electron ring in plane, and you go, ooh, this doesn't fit very well. So the electron ring will be slightly tilted. It's just it's tiny. I'm not even sure it's more than a degree, but they're going to tilt it. Why? It gives them a lot more space on this side of the machine. And if I take a ring and tilt it against another ring, I can still have 2 points of contact. I need 2 points. I've got 2 interaction regions. Perfect. I give myself a little more space. I don't have to make the tunnel any bigger, but I had a little bit of space I could go up. So they tilted. This always was fun, not only in physics, but in engineering, right? It was like, once we came up with this, the engineers were like, we need a little more room for magnets. And yeah, people come up with really clever solutions to things.
Yeah, and the way how they operate, they defocus and then focus the device. They defocus and then focus. They focus in the horizontal plane, they defocus in the vertical. They have to do those operations. And then there is a sense of some equipment necessary for the polarization. and they cannot do it till for the.
I saw another question here.
Oh, yeah, one thing that I was wondering is part of the reason that EIC or Brookhaven got the EIC, because just looking at it, seems like it would have been easier to kind of build it at Brookhaven than building something that based on the picture, looks like it's bigger than the current accelerator is at JLab now. So is the Brookhaven upgrade like cheaper than building it at
Yes,
JLab?
about cost is indeed one of the things that was considered. And this is a much bigger electron ring. This doesn't have the same scale. So you could put this entire facility inside the circle. But nevertheless, this was a less expensive option. At least if you weren't interested in the polarized deuteron. So what's not in the baseline of the project in physics I would really like is doing polarized deuterons. That's going to require more spin rotators. So once I have all the additional spin rotators, am I up to the cost of this? I don't know. But there's always a practical question, which is, okay, sure, maybe over the course of 20 years, the integrated cost of this might be cheaper than that. I need to get it built. You know, I want to get it built in a reasonable amount of time, and I'm only going to get some, reasonable or realistic increase in budget to make it happen. So you got to take in all these things. So this is a less expensive design, perhaps a little bit less risky. This was a little bit novel. It is interesting to note that the Chinese Electron-Ion Collider has latched onto the figure-8 design. It is very clever. If you're building from scratch the ion rings, the figure-8 design is clever.
Okay, I'll stop here just because time is running. So thanks again, Doug, for the talk.
Also notice that out of the 7 young scientists that were shown here, 4 were former HUGS students. So you're up to this stuff.
I have 2 communication before we have a 10 minutes break. I think it's 10 minutes time. Okay. The first one is that I still don't have all the seminars and all the poster, so all the abstract. So please submit it. This is not. I mean, we said in the online that is strongly recommended. That means that is mandatory. I mean, you're here, and it's really a good occasion to do this thing. In particular, if it is your first time that you give a talk. I mean, I did a talk in summer school like this. For my first time, was terrible, but is like the starting point to start to learn how to do it. The second, that is more for people only here in this room. So if you want to subscribe for the tomorrow, how we call it, the excursion, yeah. So please thumb up on the Malte message so we can organize it. The idea is to go in the afternoon around 2 to tomorrow. We start around 2. The weather is not super hot, so it should be fine. But get with you some solar screen and protection and whatever is.
And water and heads and water.
And water. I mean, there is also beer, so we're going to Does it work? Yep. Okay. So let's start. I know it's a long day, very tough. So now we have our second topical seminar on EIC detector with Yulia, that is a staff scientist here at JLab. So Yulia,
Yeah, thank you. I hope you can hear me well. So let me introduce myself. So I'm a JLab staff scientist, and I'm working for EIC for, I don't know, maybe the last 6 years or so here at JLab. But my prior background was HERA, and as you know, the HERA is the first called Proton Collider, which was built in the world, but it's not operating anymore. But you know, now I'm advancing to the Electron-Ion Collider, so something similar, but you know, the same concept. So it's DIS detector, DIS experiments.
sorry, Yulia, before you start, can I check this is working?
Just a little soft on mine.
Maybe I need to go here. Is it better? Is it better?
It's okay. It's a little soft though.
I
Maybe would you mind just being a
Go
little
to
bit
this
closer?
side. Okay.
Sorry.
yes, thank you.
Okay, let me start here. So here's outline of these presentations, and some of you know, things which I have here in my slides was already introduced by Douglas. And I just would like to remind that, you know, the materials which I used, it's a really like EIC community effort, which we had the yellow report and the EIC project. And these are the 3 proposals which were shown. So I just wondering how many of you have the experimental background in the detectors, and oh, quite a few. Oh wow, almost that. So you probably know this formula, right? So what do you know? What we want to have from you know, our detectors from our experiments, as many events as possible, and there is some contribution in terms to this formula. So cross section is given by the block, so we cannot really change it. We need to have you know, high luminosity as possible. So this is what the EIC can provide for us. And there are the 2 parameters which really relates to the detectors, and the one which is what we call the detector efficiency, and one is the acceptance. So for the efficiency, normally when we talk about the efficiency, we say that we need a detector which has no dead time. That means, you know, everything what events will come, it will immediately, you know, will store. And for the full acceptance, we want to detect all particles, right, which comes out of the condition. And now I just actually want to go with you through all the questions which we had recently when we really designed the detector. I was a part of the Athena, which was not selected, so this is the second disappointment for me, because JLab was not selected, and now Athena was not selected. But you know, the concept is pretty much the same, so that we go all together with you, and we'll try to answer the questions. Yeah, please.
Maybe I'm getting it. But I was wondering where the 3 Tesla magnet was going to come from for Athena.
So Athena was 3 Tesla magnets, yes. And
where was it going to come from? Were you going to build it?
so 3 Tesla was completely new magnet, which our colleagues from France, you know, worked on the design, and it's, you know, brand new magnet. With Eche, you know, as you heard from Douglas, that they decided to go for like reuse of the magnet, and it's 1.5 Tesla. And I will come, you know, to the challenging parts later. But as I mentioned, right now I just want to like, you know, go step by step, and like sort of we will design the EIC detector with you together. And right now there is still time to do the changes. Actually, we are living in really good time when everything is, in the simulation and we can simulate it, but it's not yet built. When I joined the hierarchical, the Zeus collaboration, it was already built and there was no way I could change it. I saw that something was wrong because this was already too late. So now we still have time, as you heard from Douglas, a lot of, not a lot of, but a couple of years ahead of us to redesign and fine tune the experiment. So, but first we have to decide, even though that we have the EIC collider, collider accelerator, we have to decide what do we want in terms of the physics. Do we want to have the fixed target detector kinematics or really the collider? So this is how the fixed target experiment looks like. So we'll have a target and everything in terms of the kinematics will be boosted forward. So all your detectors will be sort of line along the one lane. And there are a lot of, at least two collider experiments which have this fixed target detector kinematics. One is LHCb and another is a Hermes here. But for EIC, we of course decided to do the full detector collider experiment. It's pretty much similar to the Atlas, CMS, CAC, the very true experiment at CAC, or H1 and Zeus. Yeah, so this is example of that. In terms of the, as you can see, the difference in kinematics. So here particle goes forward. Here, in terms of the collider experiment, they go to the 4π. Yeah, so that means we have to cover everything around. And this is the exercise which Douglas told you. So you can do this at home, and just to compare the benefit of the fixed target experiment versus the collider. So now we decided that we will do this, total acceptance detector, the collider type. How should we do? So what is really like limiting factor? So you have your ions coming or protons coming from one way, electrons from another. So they collide. There's some particle scattering, and of course, that you have to deliver the beam, right? So there's of course will be some limitations because there will be beam elements here and there which will limit the space, and you will not be able to squeeze any detectors. So, and that's also define what the size of the magnet you can build here, and of course we are interested not only in the particles which goes into the central detector, but because of the GIS of the kinematics of GIS collision, so we also interested in measuring the luminosity or measuring the scattered electron which goes under the very small angle, and of course the remnants or the exclusive physics for the outgoing proton side. And it's really important, and what we actually started at EIC from the very beginning, that it's really important to keep the integration with the accelerator at the very early stage. So we had thousands of meetings with our accelerator colleagues explaining them why it is important to keep this design and why it is important to provide some space for the detectors in this area. And because it's electron proton or electron-ion collider, the forward, this electron going directions and the hadron going directions are completely different. They will serve completely different purpose. And this we also have to keep in mind when we design the detector. So this one will be mostly responsible for detecting the scattering electrons. Well, in this area, mostly, the main task will be to detect jets and the remnants from the proton. So this you've already seen. So this is the kinematics. We have several, let's call the parts of the detector. So we have a barrel, and barrel actually what we call is this part. So if you talk about the observed rapidity, all the detectors sitting from like pseudo-rapidity -1 to 1. This is what we call the barrel. Then we have the electron and cup, where the all the scattered electrons will be scattered to, and we have the hadron and cup. And of course, we need to also map our design of our detectors to the X and the Q square plane, and understand really what like energy of the scattered electrons we're expecting to get and where, right? And so this is the plot actually showing what will be the energy of the scattered electron. So this is a constant line or isoline, and also showing also with the color the areas of the forward and the barrel area where this scattered electron will be scattered. And as you can see that mostly all our scattered electrons will end up in the electron end cup or in a barrel, right? And the higher the energy, it will sort of bounce to the higher and higher energy. Sometimes it will also bounce back to the hadron and cup, but it's really rare, and it will cover only the very high Q square area somewhere over. And for the hadrons, it's actually the opposite. Yeah, so they mostly will end up either in the barrel or the hadron and cup. And the higher the energy of your jet or your hadron, the more higher X or higher Q square it will be. So now let's answer the question, why do we need the magnetic field? You know all this, the formula, magnetic field, we need to measure the particle momentum. So when the charged particles inside the magnetic field, and in this case, the solenoid, it will start, twirling, and this motion, what we call the helix trajectory, right? So let's start moving along inside the solenoid. And what we do in the experiment, so we are measuring the bending radius or bending curvature, and using this formula, simply this simple formula, we reconstruct the momentum. Now the question about the solenoid field. What is the strength, right? If we have the too strong magnetic field, then all our particles will start sort of curling, and low PT particles will go along the beam pipe and will be undetected. Yeah, so simply we will lose all the low PT particles. They will simply go along the beam like shown here, right? But if we have too weak magnetic field, then high PT particles will just simply go straight, and we will not be able to reconstruct this bending radius. In this case, we either need to have very precise or high granularity detectors so that we can really distinguish between the different momentum. But of course, the higher the resolution, more expensive it is, right? So we have to find it out. So another thing is to remember that solenoid we need only for the detector system. Accelerator do not need a solenoid. For them, it's even worse. So they need to compensate it, because when the particles goes along the solenoid field, it will see some magnetic field, and you need to correct it in order to keep on the orbit. So for them, it's even the headache. Yeah, so they try to think how to compensate it. Yeah, and of course, you need to optimize the size, right? Douglas already told you that if you're building the detectors inside the hole which already exists, so how you really move the detectors in and out for maintenance. So you have to really see that everything fits together. That it's the bore of the solenoid is large enough so that you can squeeze all the detectors inside, and the length is enough to measure the potential. Okay. So finally, it was chosen the Babar solenoid magnet. It has 1.4 Tesla field, and this is the diameter is 2.8 meters and the length of 3.4 meters. So everything fine, but what is the problem? Yeah, so we can spend the, we can save the money because, it's already existing magnet. We don't have to spend extra money for that. Problem is that it's sitting at the AP8. And the experiment which we are building is at AP6. So now we have to disassemble everything and ship it and move it to the AP6. Yeah, so this will be additional money and additional risk because during the transportation something may happen. Yeah, so this is sort of the way you balance your cost, risk, and all this. So now let's go to the detector design. So central detector design, so this is the general purpose detector as all the particle physics experiment. They have tracking, vertex, PID, colorimeter. Some of them have a muon system, so we are not planning to have one. Yes?
So as I understand that the Babar magnet will be used by S-Phoenix first.
They already using it.
Yeah, and then the S-Phoenix has to shut down so that HR can use the Babar magnet.
Yes.
In that meantime, Star has already shut down and IP6 is free.
So AP6, yes, they will clean up AP6 hole, and then they have to disassemble S-Phoenix and ship the magnet to the AP6.
So S-Phoenix stops taking data after Star has stopped.
Yes. Because Star will need to disassemble completely the whole, yeah, so they have to. Yeah. Okay. When I mentioned to you that we need to measure all the particles. So measure all the particles means that we need to measure particle momentum, the vertex, energy, and the time, right? So by measuring all these four, we can identify the particles, right? And like we can fill this four vector with corresponding properties. So if you look at the data particle group, we have 200 particles listed there. Have you seen this? It should be your, the book of the particle physics. It should be on your table every time you open it. But if you look carefully, then you will see that only 27 have the lifetime or can travel more than before the decaying more than 1 micron, and only 13 have a lifetime greater than 500 microns. So that means we have to really concentrate on the detecting of those 13 types, right? So not bad. So we are already going down from 200 to 13. But how we identify the others? Of course, the others we identify by looking at the invariant mass of the final state particles. And this is example of the D0 going to the pi k. And this is a question coming, how well we should measure the particle momentum. And this is sort of gives you an example. If you take the Monte Carlo samples and you plot an invariant mass of the D0 by just combining those two particles, you will have the delta function, right? But of course it's the ideal situation. But when you start putting the smearing parameters into your momentum, you immediately see that this invariant mass peak started to get broader and broader and broader. And if your tracking detector do not really reconstruct momentum very good, you simply will not be able to identify this T0 particle. So that means for the EIC, of course, we would like to have here, but the light showing that we cannot really go as good as at that. So let's move to the tracking detectors. This is example of the tracks in life, and this is how the tracks looks in the particle physics world. Of course, all particles need to interact with the material of the detectors, and the way how they interact is described by the Göteborg formula. I will not go deeply into this, but just for you to as a reference how it goes. But I just wanted to highlight here what is really we need from the tracking. So we need to have the electronically recordable hits, because of course it's good to have these pictures, very precise. But nowadays, if you would go to this, the photo emotion, we need 1 million scientists who will do the analysis of those pictures, right? Of course, we would like to do everything on a computer, so we need the electronically recordable hits. We need to provide they need to provide really precise space points or the trajectory measurements, and we, of course, the momentum and magnetic field. We need to measure angle very precise, and what is really important is to really reconstruct the primary and the secondary vertices. Multiple track separation, of course, it's important. You have to understand if it was 1 or 2. Provide, if possible, particle identification, and of course, the keeper material at the minimum level. Why we need to keep the material in the minimal level? Because again, it comes to the fact how the momentum resolution goes. There is 2 terms in this formula. One corresponding to the position resolution of your tracking. It depends on the magnetic field, on the length of your detector, and on like number of hit points which you have along the particle track. And the second term is a multiple scattering. It's actually, really depends on how many materials you have. And when the particles go into material, it starts, experiencing multiple bending. And of course, the changes trajectory and lose the energy. So we would like to keep these terms at the minimum. And on this plot, you immediately see, that you cannot really do the sigma p over the p below these multiple scattering terms, right? So if you just do, this conversion of some of those terms, you immediately see that this gives you the limit. That's why we would like to, minimize the multiple scattering so that we can improve. And also we need to reconstruct the vertices. And just for, I mentioned that the D mesons, they have decay lengths of 100 microns. That means we have to reconstruct vertices coming from the D stars from the original sort of the 0 vertex. And the 100 microns is the thickness of your hair. Yeah. So you can imagine that we need to reconstruct 2, identify the 2, separate 2 vertices in the size of your hair. This is the the detectors we are right now looking to. And the problem is that at the EIC and actually at the old collider detectors, we cannot place the detector as close as possible to the interaction region. So there is a beam pipe, and the beam pipe is actually 3.2 centimeters in the radius. Yeah. So, and you need to place the detectors with such resolution so that we can sort of back trace or extrapolate your trajectory into the interaction region with the precision of better than 100 microns. Yeah, a little bit about the beam pipe. The inner section. So this is the central detector. I think it's plus minus 4.5 meters. As you can see, because of the crossing angle which we have, it has weird structure. So this will be the straight section made out of beryllium, so that the particles going sort of at the 0 rapidity with low PT will experience like less material, and then the crossing angle. So this will be the way. Of course, for the forward-going particles here at the end, at the edges of the beam pipe, we will have the thin window just to sort of make sure that Oh, yeah.
Will the like a 1.5 Tesla magnet in the center have any effect on the path of particles along the beamline. And they'll have effects on the particles that come after the collision, but what about the ones that are close to the interaction point along the beam?
I don't know if I got the question correctly. So the one which goes along the trajectory, or you mean the bunches of the accelerator?
I'm talking about the ones that would be very close to the interaction point, but you have like an extremely like strong magnet there. So would that magnet have any effect on particles in the beamline still, just moments before they collide?
Of course, they will have some. Yes, they do. They will experience some field. So the bunch or accelerator bunch has a profile, so it has some shape. So yes, they will have some. And of course, you need to compensate it. What I mentioned. So you need to compensate this kick, which solenoid gives to the accelerator bunch, in order to keep everything on orbit.
So in the case of a collision with an ion and an electron beam, I mean, I understand you have the issue of the primary vertex and secondary vertex, but what about pile-up corrections?
At EIC, this is the beauty of the DIS. There is no pile-up. There will be only one interaction once in 500 collisions. So the EP or EA little bit different, but there will be no multiple events in one when the two bunches are colliding.
I understand that you're EP, but EA as well.
EA will be a bit, it's not like the AA collision at LHC, yeah. So there will be some, but not like every collision which we have. The EP collision, so the DIS event is quite high PT, which you can be detectable, will be once out of say 500 bunches. So you will have some time to store your data. For EA, maybe it will be not 500 bunches, but like, but there will be no multiple events. Maybe they do sometimes, but not regular. So this is the tracking system at the EIC, how it was designed. Again, you can see that we will have the vertex detectors, layers, then the outer layers, also based on the silicon, and MPGT based micro-orbital technology before and after the jerk. And there will be also silicon disc along the beamline and the end caps for the forward and the backward particles, and there will be also the ACA dot, which will provide the type information. Yes, and as I told, we need to reconstruct the tracks and everything, regarding the reconstruction and the simulation, what we are using. There will be a separate talk by Dmitry Romanov. Okay, and we need to keep the low material budget. So this is what we are expecting to have per layer in terms of this vertex detector. And they will have the 10 micron pitch. It will be based on the ALICE ACTS3 technology maps. And yeah, this is sort of the geometry which we are going to have. So if you're looking at plotting the distance of closest approach with such configuration, so as you can see, depending on the momenta, we will be able to sort of go down to the 10 microns, maybe for low momenta, it will be around 100. But it will be enough for the outer detectors, micro Arwell, resolution is around 50 microns. Even though that we have the granularity is around 100 micron or 400 microns, I think. And this is the sort of the final fundamental resolution which we are going to achieve with this type of detector. of course, when we talk about the tracking detectors, we need to really reconstruct the tracks. And what is really important to keep the synchrotron radiation under control, because there will be a lot of ghost hits. And if you start to reconstruct the track with a lot of the ghost hits, it will be really challenging. Right now, people are thinking of using like machine learning tools to do this, but it's probably for your generation. We didn't succeed yet. And of course, the beam gas, we need to keep the vacuum under control. This is how the beam gas event will look like in the EIC detectors. So like random hits, random tracks. And of course, there will be some slow neutrons. So everything needs to be under control here. So let's switch to the particle identification. As I mentioned, 13 particles, and this is electrons, positrons, gammas, so jets and special types, with like number of collimated particles. We have the individual hadrons, pions, kaons, protons, muons, neutrinos, which we are not detecting, but we are detecting it by measuring the missing T in the electromagnetic and Hedronic colorimeter, and the neutral hadrons in the Hedronic colorimeter. So this is the way sort of the how you identify. Why do we need actually the hadron identification? So this is the main question, like why do we need to identify individual hadrons? And this is one of the examples. This is one of the processes which we are going to study at EIC, which calls boson-gluon fusion. So if you do not have the PID or don't have the vertex, you simply do not see any invariant mass. So it will be filled with a combinatorial background. And another example, so if you start to introduce a little bit of the particle identification and the vertex, you can immediately see that, out of this, continuous background, you have a nice peak of what was a D0. Yeah, so that means we need to really identify the particles in order to make the correct combinatorial combination. When you plot also the momentum of the particle as a function of field rapidity, you immediately see what was the range needed at the AC to identify the particle. So this is the pions and the kaons. As you can see in the electron-ion path, we only have the particles with momentum 10 GeV. Goes down in the central rapidity, while in the hadronic and curve, where most of the hadrons goes, it goes up to like 57 GeV. And this is how we actually design our PID system. It's mostly based on the Cherenkov detectors, so that we have a dual radiator reach, responsible for identifying high momentum particles. We have a jerk in the central detector in the barrel, and modular reach in the electron and cup. And this is how they look like. So this is the backward directions, modular reach. It covers pi to k up to the 10 GeV and has a modular structure. We're still discussing if it will provide if we are going to keep this technology or not, because it's quite massive, and this area we would like to really minimize the material. For the barrel, we have a jerk, so it's radially compact detector. It's only occupies like 5 centimeter space, but it has some expansion volume, and it covers up to 6 GeV. And for the forward PID, we use the dual radiator reach. It has the aerogel and the gas component into it. And as you can see that it's covered really the full spectrum. Yeah, so still under question what kind of readout we are going to use for the PID. It's actually not only for PID, but also for the colorimeter, either PMT or SciPMs. There is a lot of advantages and disadvantages to the different technologies. Right now we are of course considering the SciPM, but they have really huge dark noise rate, and that might potentially create a problem for our data acquisition system, because we are planning to have a streaming readout that means we're going to transfer all the data, all this noise, and this potentially could be the bottleneck. Also, for the timing, we need like time of flight detectors, and this is example how the time of flight detector works in like fixed target experiments. But at EIC, so we have a collider kinematics, and there are a lot of questions about like what should we do as a start of the detector, like T0, right? Because we cannot really like trigger our detectors at the collision. So what we are going to use, and there are several methods how you're going to do this by, and actually right now it's done by measuring the lengths. That means you have to really identify the very precise the vertex so that you can, minimize this uncertainties on your particle length. And of course, you need to have very precise the timing for your time of flight system, the order of like 10 to 20 picosecond. Yeah, so picosecond. Yeah. And the ACL GUGS, which we are currently considering right now, so the prototypes show that we can provide 20 picosecond. Better than 20 picosecond resolution. In other detectors, this is actually my favorite because I'm working for this detector like all my life, is the transition radiation detector. It's used in addition for the, in addition to the Cherenkov colorimeter to identify your electrons. And the idea is here that, the electrons, when they travel through the detector and this inside this radiator, they produce the transition radiation photons. And just, by looking at the extra energies which is produced by this type of detectors, you can sort of identify it. And this is the setup which we have actually here at Jefferson Lab, where we're testing the polarity. But it also provides very precise track. Why do we need the colorimeter? So of course we need the colorimeter. You can say that in principle for the charged particles we don't need this, right? So you measure the momentum and you identify the particles, the PID, and you sort of knows the energy, right? So like why do we need it here? But I can say that it's not always possible to identify the particles. And sometimes, your momentum measurements are not really, at the very good level. And here is an example, right? So your tracking resolution goes like linearly, while the resolution of the colorimeter is sort of shape. And at the certain, depending on the resolution of your colorimeter, at the certain areas, you can see that the colorimeter can provide even better resolution. So why do you want to use the tracking information if you have very precise colorimeter? And also it provides measurements of the energy for the neutral particles, right? This is the only detector to provide energy measurements. So this is like, why the colorimeter, what we call it. And as you know, the colorimeters, the energy measurements are really destructive. So that means you stop the particles in there. Yeah, after your colorimeter, only muons survive and neutrinos. And that means you have to have all the detectors, before the colorimeter. So this is colorimeter is sort of the outermost detectors. For the EIC, again, we would like to have the 4π coverage, it's like the must. This is sort of the layout of the colorimeter. At the moment, in the current configuration, as you can see, the electromagnetic colorimeter, we have the 4π coverage, so the viral part, the electron cup, and the hadron for the hadron cup, and this is the hadronic colorimeter. You can see we don't have electron type hadronic colorimeter, but it's possible to do this as an upgrade. We are even thinking about including this to the baseline. So this is the sort of the technologies which we are planning to use for the electron end cup. We are planning to have the crystals because they provide. And in electron end cup, we need it because this is the area where we have to detect our scattered electrons. And we need to really measure it precise. Yeah, so the best colorimeter possible in the electron end cup. And then we can, for the electromagnetic colorimeter, we can sort of restrict, or we can have the other technologies. And one of the technologies is that side glass, because the constraints on the resolution is not as high as for the electron end cup. And for the forward going part, we are planning to have the I probably will skip, you can read it. So we have a lot of progress recently on the glass. So glass is an alternative technology to the crystals. We have a lot of progress within a couple of years in the building and fabrication of this. With the lead tungsten, we still have to select the vendors right now, because Russia is not producing this, and we need to really grab the correct vendor. And so this is an example of sampling colorimeter. So sampling colorimeter provide the resolution around 7 to 13%. While, as you know, I don't have it. For the crystal, it's around 2% or square root of E. Again, this is for the HCAL. We are going to reuse what the S-Phoenix have for the for the HCAL. So that means we are grabbing the magnet together with the hadronic colorimeter, and this is the idea of hadronic colorimeter for the forward going direction. As you can see, that this is the energy resolution, which as you can see in the barrel, the depth is quite small because we cannot squeeze it inside the door. Yeah, and this we want to increase it a little bit, but the energy of particles are not so high here, so we probably don't need.
Sorry, Yulia, you have still 5 minutes.
Oh, 5 minutes, that's good. Okay, then I am going to, yes, so material budget really important. Let me introduce a little bit the forward areas. As you can see, so this is a central detector, and we have the forward going area and far backward area. And this is the element, the accelerator elements, quads, and the dipoles. And I'm just going to show you a little bit on that. And on the electron going side, we have the luminosity detector and the low-Q square taggers. So for the far forward, so the IP is here. So this is sort of the end of the central detector. We have the B0 dipole, so it's dipole provide the field, and we have the silicon detectors inside, so that we can really measure the momentum of the particles in this area. And we have after this quads, we have Roman ports and the off-momentum detectors. They will be integrated inside the V5 and the 0-degree color. So I probably will skip this one. So the B0 detector is really complicated. So this dual function magnets, so crossing angles, electrons and hadrons going here and there, but we still have some space to place a detector. So it will be challenging in terms of the mechanical integration, but we will do this. For the Roman ports, we are planning to have detectors inside the beam. As you can see, this is a cone of the particles, 5 milliradian cone, hitting the Roman ports, and they will have to really go very close to the beam, 10 sigma away from the the trajectory of the beam, and they will be movable because we do not want to really burn the detector, so we will move them out during the injection, and this is really we are working on the mechanical integration. It's really work together between accelerator and detector systems. Douglas showed you the scrap cavity rotations, but due to the scrap rotations, this introduced also some angular smearing and the vertex smearing for the particles going into the forward area. That means we have a lot of uncertainties in this area, but so right now the work is going on to sort of optimize it and make sure that we have the enough resolution for the detector so that we can sort of balance this. Why we have a two system? This is good examples coming from the DBCS process. So as you can see, the B0 detectors and the Roman pods actually provide the almost the full coverage for the forward-going particles. So this is the forward-going particles, and this is what Roman pods will measure and what the B0 will measure. And if you go to another energies, you can see that one system or another started to take the lead on the detecting one or another particles. We also planning to have the off momentum detectors because those particles have in our accelerator we will have the protons which comes from the nuclear breakups, and they will have the different magnetic rigidity. That means they will be bended strongly, and we need to have the detectors over here so they will not reach the Roman pod. So we need to detect them earlier, and we call them off momentum detectors. Another the sort of the idea, or not idea, but the types of the particle we could have the lambdas, which is decaying, right? And for those we need to have another set to detect the negative of ions because they will be bent in the opposite direction. So it's still under discussion if we want to have it in a primary design or in inside the after the upgrade. 0-degree colorimeter, very important, so it will be seen. So this is a central detector, so you can see the scale, right? So this is a central detector, 9 meter space. Then we have the V0, and then the crystals with the whole final focusing quad, Roman pods, off momentum detectors, and the CBC, so sort of the final detectors. I probably do not have the time to talk about far backward region, but as I mentioned, that low Q-square events like a photo production with Q-square below 1 will end up in this area. So the electrons will be detected here, so far away from the central detector. And of course, the luminosity detectors we need to really know. You can look at the slide. So I will skip the polarization and data acquisition. So this is really important. We are planning to have the streaming readout, and this is really important to keep, make sure that we can really trace all what we need into the disk space. So this is my summary. Actually, I wanted to show you something very quick. Do I have minutes?
I think let me see.
We have, the colleague of mine who worked on, this is Athena detector. Yeah, that is fine also. You can click on the start if. Can you play? No.
Because the problem is this.
This is a PDF. Okay, so I will upload the PowerPoint so you can watch the nice video showing the collision. And, it's a 3D, so you can really look at the slide and walk through. Yeah, but of course we do not have a 3D design, but it is the video you can watch. Okay, questions.
This is just I guess kind of like a more general question, but whenever I guess like an old particle accelerator goes down, or like an old piece of equipment is taken out, are those like usually recycled or like kind of repurposed in other places? Like for example, for like, you said that Hera, went down in 2007. So did they take the pieces from that and use them for something?
Yes. So some of them yes, some of them no. In principle, colorimeter or the colorimeter, the solenoid can be, repurposed because it's a solenoid. If it's operational, why not, right? At ZEUS, we actually had very nice hadronic colorimeter, uranium compensated colorimeter. This is the best colorimeter in the world ever built, in the entire, era of the
Human era.
Human
We don't
era,
know
yeah.
about gallium nitride.
So it was with the resolution is 35% of the square root of E. 35 uranium compensated, yeah. So I provide extra radiation in order to compensate the losses of the neutrino center. Can you repurpose this? Yes, you can, but ZEUS paid I will not say the exact numbers, but a lot of money to ship it back and store, in some, the garbage containers, underneath somewhere in Utah, I think, or somewhere. In principle, you can dig this out and you can, place there's like nice crystal bars. You can, polish it and reduce it, and probably, but they're not using it. Why? I don't know. Because at that time there was no transition between the HERA and the EAC. Probably, if the EAC would start right after the HERA, they of course will reduce it. But yeah, the gap of 15 years. Yeah. But some tracking probably you will not use because it's first of all old and aging, and you probably want to have something brand new and like state of art, more flexible. But some of the equipment you can, like robotics. Yeah.
Would having a 3 Tesla solenoid actually be advantageous? Because you said that, for example, some of the particles would just spin out basically without being detected.
So with the 3 Tesla low PT particles, there is a, if you look at the spectrum, right? So it's not like you pick up a particular. So there is a PT spectra. So with 3 Tesla, you will not be able to detect a low PT, right? With I think at ZEUS we had a cut of the 50 MeV. So in this case, like 50 MeV will be lost inside the pipe. But you detect the high PT and will measure with a high resolution. Yeah. Also, the 3 Tesla will help you to detect the particles going along the beam line. You need a stronger field because they will have a higher momentum. So you need a stronger field in order to sort of keep them a little bit so that you can detect them. So in this case, the 3 Tesla is a really advantage. But for some physics, like the D-star, if you have a slow ion, probably you will lose this physics because slow ions below like 100 MeV.
Cost like aside and everything, would it be advantageous to use like a bearing magnetic field, or would that just add a degree of complexity that's not worth it?
The cost, you mean?
Yeah, if like you just ignored costs and stuff.
So it's my personal taste, I would go for the new magnet. But right now, as you saw from the Douglas, we are thinking about having the 2 interaction regions. That means, we can repurpose, the old magnet and save money for the first detector, but build the new one for the second detector.
Yeah.
So in this aspect, it's sort of the balancing between,
Yeah, that would have been my second question.
Yes. Yeah. But from other hand, so I'm from Latina Collaboration. We propose the 3 Tesla, and I, personally think that you're building the machine, which is the like $1 billion accelerator. Why you want to reuse the old equipment, right? So why don't you spend on and really build the, the state of art detectors? But of course, everything, is money, right? So right now we are trying to get the collaborators from the entire, the world, so that they can also contribute to the development. For the 0D colorimeter, actually, I didn't mention it. We have really state-of-art detectors. which is silicon, so that, you know, will provide really do you have a picture? Can you scroll it a little bit?
Yes.
So it will have the several sections, and will have the silicon imaging layers in between, but then the cost of this thing is 60 by 60 is 5 million. So imagine if you have to, you know, cover like, you know, the 9 meters for the entire collider space. So it's, yeah, right now, so probably maybe for the next generation, probably for the FCC, it will be possible. But right now, we probably can afford only this one.
So as you said, there was a competition between Athena and HR, and then finally HR got the money initially. So now let's say HR gets established, the motivation is shown, and then DOE gives you more money. Then so now the people involved in Athena and HR are working together for the HR experiment, right?
No, right now they're working together on a detector one. So there will be new
Detector.
collaboration, and we will have a probably new name.
Okay, so now let's say you get more money and then the Athena comes in.
No. they usually, you know, try to, you know, cut the money.
So you're
No,
sure
they-
that would not.
No, there might be a lot of contribution from the you know, institution around the world which who wants to really contribute, but probably yes, we will have a little bit more money if we have more you know, contributors, but you know, still we have to sort of baseline and make sure that like if, for example, right now all the borders will be closed and there will be only US, you know, we need to build this sector in order to have this project running. No, there will be limited, you know, amount of money which we can spend, and we have to optimize it.
We have another question for that.
Have they considered a liquid simulator design, like Atlas? So I've heard of, wasn't it Atlas chose it because it was cost effective?
Not at the moment. So we are not actually really like optimizing the cost, but we are also optimizing the performance, right? So we want to, you know, some areas where we can sort of, you know, have like traffic technology are not really like, you know, very, very good in terms of the resolution, but, you know, in some areas they can work, you know, why not, you know, can keep it there. But in the electron-ion cup, we really would like to have the, as I mentioned, the electromagnetic calorimeter, which is the best resolution.
Other questions, comments? No feedback? Okay.
All tired and want to.
Okay, so see you on Monday morning at 9, and for the people that are coming tomorrow,